Test, test, test.
Well, good morning, everyone. Am I hearable enough? Yes. Okay. For the first talk of the day, we have Andreas Krupelin. He's a PhD candidate at the University Hospital in Jena. His work focuses on computational biology. And without further ado, let's introduce him.
All right, thank you so much. So, good morning, everyone. Good morning to the live stream as well. So, you are in the correct room and the correct stream if literate package development using Pluto is what you want to hear. So, I will quickly introduce like a strategy that I try to employ when using packages because I like using Pluto, and I kind of assume for the sake of time that you're like familiar with Pluto. And that you're also like the kind of person like me who just wants to do everything in Pluto as far as possible. So that's like the premise of this talk. The other way you can view this talk is as a very lengthy introduction to the talk that will start in 20 minutes from now by Alberto, where I think we will learn about all the technical details behind what we're trying to do here. So, just for the sake of an example, let's say you've just came up with a very great new probability distribution that somehow is magically appearing all the time in nature, and your name is Carl Friedrich Gauss, and now you want to investigate this. And of course, you want to do this in Pluto because that's your favorite Julia IDE, basically. And why would you want to do this? Well, as I said, I think most of you are aware you can have like nice text and include some math, and then you can write your actual code. So, for example, you maybe define some type for your distribution, and then some methods on that, so you can like evaluate the probability density function for this or so. And then you actually want to get into the really nice properties of Pluto, and you have this reactivity, right? And then maybe you need to use some Pluto UI sliders and say, well, I wonder what happens when I change the standard deviation. Oh, interesting. Okay, then the PDF at 0 changes a bit, and maybe you also want to see how this behaves in a graph, and then you plot something, and you, like one of my favorite features of Pluto, you can just reorder the cells, and you can say, how does the graph change? Ah, interesting. Okay. So you have all those nice things that you use to investigate your topic of research in Pluto, and maybe you also want to use some external libraries. So let's say you not only interested in the PDF but also the commutative distribution function, which you might, if you're not caring about efficiency so much, implement using like an integral, and then you want to do this numerically using the quad GK package. Just let's say for the sake of an example, so you use this package and then implement some functionality, and then all right, okay, so the CDF at 0 of the standard deviation, standard normal distribution is half, so looks okay. And now let's say you realize that this might be very useful. Like, okay, so normal distribution, maybe other people also want to work with the normal distribution. So the next best thing that you would do in your Julia workflow is to make this into a package. And I think maybe the canonical or most obvious way to do is to like start a new file from scratch and then copy out all the relevant code from this notebook into this file, right? So what is relevant? Well, probably this definition of this function is relevant. But this here on the bottom, that's not relevant, right? I mean, that's just for your own trying out stuff. And also this plotting, like that's only for you to investigate this distribution, but someone who just wants to call your functions is not interested in any like, plotting stuff. Like maybe they do it on their own, but like not in your plotting. So and then also like this type and this PDF definition, that's relevant for others, so they want to have this. But if you just now take all this and copy it into a new file, this has some problems, but because I mean this is like cutting edge research you're doing, right? So it changes and you develop new things and have new ideas, and then you have those new ideas in your notebook, but then maybe they're also useful. You also want to put them in the package, and you have to copy all that again to this package, and it gets out of sync, and you have to be really aware which code is where. So what I propose is that you actually stay inside the Pluto notebook and make this Pluto notebook into a package. And the rest of this talk I will show you how you could go about doing this. So what you start off is you go into your Julia REPL, and I've already prepared something here, so it's like a bit of a cooking show. And you create your your package, just as you would do, like either do like the package generate command in the package REPL, or use like package templates or whatever you like to do. And then you make sure that you have three dependencies in your package. The first one is Pluto dev macros, and this is the one that you are going to learn about more in 20 minutes. And this is like what does all the technical details behind this. And then you have two other packages that you always have to use, which are interactive utils and Markdown, because every Pluto notebook like automatically depends on those two. You just have to make sure that they're that you have them, but they understand the library anyway, so it's not really a problem. And then additionally, you also include all the packages that you use for your code. So here we used QuadGK for this integration, so you also include this. And then for the package definition, all you do is like you just use this those include functions, put in your notebooks. And what are those notebooks? Well, in those notebooks, you have like this is more or less the notebooks we just saw, but you use the Pluto dev macros to include the packages, and you have this fancy syntax where we're going to learn about more, where you have this way of including your packages, and you can also include stuff from your own package. So this is like inside this package, and we have another notebook where maybe I define all my types. So maybe you want to split this up into multiple files, and you can have it like this. And then like the last important thing, because before I stop, is that all the things that you don't want to have in the package, you can disable them in the file, right? So in Pluto you always have this disable in file, and this is what I did here. So for all the the plotting stuff and the interactivity stuff, I disabled them in the file, so I still have it in my notebook, can use it here, can investigate, but the user of my package won't have to use this. And that's all the magic that you do to have the package development in Pluto.
Thank you, Andreas, and also for keeping it on time. Are there any questions from the audience?
Thank you very much. There's this automatic package dependencies. How's this kind of working together with having it as part of a package?
What do you mean by
like
automatic?
in Pluto, we have these two styles of managing the dependencies, and it seems like you haven't switched the style. So I guess the normal Pluto magic, like it's tracking the dependencies, is still active. But how does this combine with the package?
Yeah, good
version?
question. So like it's both actually. So for example, this Pluto Podly and this Pluto UI that you use for interactivity, those are actually still managed by Pluto. Like you have this in this notebook, you still have all this Thomas stuff, and so for those. But all the like functional dependencies that like I want to have in my package, they are handled differently using this Pluto dev macros, and like it itself then switches off the Pluto handling like behind the scenes and uses something else. And at the same time, when I evaluate this not as a notebook but just as a normal file, then it will just make this into a normal using command, and I don't have to worry about this. So it's both.
Thank you. Yeah.
We have time for one more question, and then we wrap it up.
I've seen other things do this with like Pluto hooks and like skip as script, or like those macros to tell it to skip versus the disable in file. Do you think this approach is better than anything with Pluto hooks? Or?
I mean, I found this most straightforward because like I use as much as possible as is built in Pluto, and then only this Pluto dev macros is what I use additionally. So I found this quite nice.
Okay.
So thank you, Andreas. Please give them an applause. Yeah.
Thank you.
Yes. For our next speaker, we have Stefan Sam. He's an entrepreneur, data scientist, engineer, and data architect. So the floor is yours, Stefan.
Thank you very much. And thank you for being here. 10 minutes is not much, so I want to rush through a couple of things. We already heard a little bit about Pluto hooks. If you don't know about them, I think that's quite reasonable. They're a little hidden, and I want to give you some insights kind of how they work. And yeah, and first let's kind of take a look at, okay, this is typical. Okay, now we are scaled to the system. So I have two notebooks kind of just running here, and the one which I put into the description of this talk is kind of running on financial data. So this is scanning Bitcoin data from Binance and running an RX infer model on top of it. We just heard an awesome keynote talk for RX infer, so it's really awesome for real-time stuff. And so this is really real-time Bitcoin data, yeah. And yeah, the analysis still takes some time, but some steps. But kind of key things to understand is that we can kind of build stuff similar to this. We can build kind of channels which really kind of grab data from Binance, and we can write a line like this. So let's see when it's going to update next. Yeah, no, it's probably. No, not that. And it's grabbing kind of data from Binance channel. And then we can aggregate this. So the key thing is really that we can build stuff like this, which is repeatedly updating itself. And we can also kind of do similar stuff, which is on a time basis. So I built kind of another macro, which is called repeat at. And these are kind of the two steps which I put together here to kind of build an RX infer model. So we get these times from Binance, from the Bitcoin data, which is of course a bit infrequent when the changes come, and we sample them again. And we do all these sampling by using Pluto reactivity. And yeah, because time is rushing, I want to kind of give you a little insight on how this is implemented, because it's not using Pluto hooks, but the underlying Pluto features. And I think it's really awesome to just have seen this once. So this is kind of the underlying key macro. It's called repeat run. And this is then kind of built on top of this. And in Pluto, kind of, if we build a macro, the first thing is that we have kind of two different runtimes, which is really cool to know if you want to do more advanced stuff with Pluto. If the macro is run, this is kind of when the cell is initialized the first time. And when the cell is repeatedly run, then this first part of the macro expansion, is never run again. Yeah, but only the expanded stuff from the macro is run. And this way we can kind of put some state into the macro, and this is how the Pluto style works. And we have usually also some fallback. If it's not running in a Pluto process, we do something which also works without a running Pluto, so that you can include it into a file. And then we can kind of have some state on the macro level. For example, yeah, let's kind of take a look, but this is really just to track us. And then we have kind of the final expression. We track whether it's the first time when we run, and then we get some special functions from Pluto. And this is kind of also in Pluto hooks. I also put it into Joel and Pluto, my little package here. But it's the very same name. Give me rerun cell function. And with this, you kind of inject something into this code, which the Pluto runtime will replace. So the macro expansion won't kind of give you this special key, but it really replaces this key, what is here, give me rerun cell function, with the actual function. And we have another cleanup function registering. And with these two functions, the rerun function and the cleanup function, we can do all the stuff. We have a hooked macro, whether this thing is triggered by another cell or not, kind of, yeah, tracking it manually, but it's yeah, and soon at the end. So doing the update mechanism, and then finally kind of returning the update every time the cell is run. And last part is kind of that we need to call the rerun function. So let's take a look here, and yeah, the rerun is called in the set update. So every time we set an update here, so then really the rerun is called. So this was a really quick one, but just that you know, so you can build this yourself by having macros, build all the states in the macro execution and kind of have in the expression object which you return some special things like rerun cell function and register cleanup. And with this you can then build all these stuff. And finally, I think the time is rushing, I'm not sure. Yeah, I also want to show you that these things actually also work for Python, not yet in standard Pluto, but I just kind of did also some extra work to make this stuff working. So at Jolin, especially at Cloud.Jolin, my focus is kind of to get these Julia tools also to everyone. And R and Julia support, R and Python support are one of my key things. And here the same is possible with some other kind of stuff built on top of it. But you can see here, this is a Python thread running in the background, just aggregating some random numbers on the Python queue. And we can do the very same, that we repeatedly grab from this Python queue and just use the Pluto updates. And this is now pseudo-random data, but yeah, it looks very similar to Bitcoin data, if you ask me. So, yeah, yeah. And yeah, RX infer does not exist for Python, so that's a case for Julia again. And yeah, so I think that's it. Thank you. And I hope you have time for one or two questions.
Yes, of course.
Perfect.
So, thank you, Stefan. Are there any questions from the audience? No questions? How easy was to use RxInfer? I'm quite curious.
Yeah, it was relatively straightforward. There's one key thing, that if you use Pluto reactivity with it, you need to kind of not use the standard way, because it has kind of its own mechanism of reactivity. And yeah, to circumvent this and use Pluto's reactivity, you kind of just need to know which methods to use. And
Okay.
yeah, but it's findable, and yeah, once you have it, of course, then it's kind of easygoing. But this was the key thing.
Okay. Oh, good to hear.
Yeah.
Oh, yes.
Are the repeat take macro, is that running asynchronously in the notebook, or is it blocking the like?
Yeah,
other
this is running asynchronously. So if you look at the repeat run macro, so every time kind of the cell is run for any reason, this code will be re-executed. Yeah, the macro code which we return. But then kind of on the update we sorry, where is it? Yeah. Sorry, I'm a bit confused here. Yeah, this. It's repeated at some time, and then it will just do the update and close itself. So to not have an ongoing running background task, but the next time this very cell is then re-triggering itself, it will spawn a new task.
And would it run on its own thread if you launch Pluto with multiple threads?
I guess it jumps then between the threads. Yeah, yeah.
Mm.
But this way this is advantage that you can disable the cell. With Pluto Hook, sometimes if you have kind of a long running background task, disabling does not work any longer that well. But if you do it this way, that you spawn the task every time kind of on cell re-execution, disabling works automatically, because the task is just not spawned again.
Thank you so much, Stefan. A big applause.
Thank you.
Hello, everyone. Good morning, and thanks for coming to this session and to this talk. And in this talk, I will introduce some tooling that I developed to ease the package development using Pluto as a tool to streamline some things. I'm actually didn't know until a few days ago that Andreas would be showing a talk using my package. I think it's the first time there is someone that I didn't explicitly told about my package that I found out is using my package, which is quite nice. So just to recap, some information about me. My name is Alberto Mengali. I have a very unique name on every Julia kind of platform there is. My job is I'm a telecommunication systems engineer at the European Space Agency here in the Netherlands. But what I'm going to talk about in this talk has absolutely nothing to do with my work. I use it a lot in my work, and I developed it to help with my work. But it's just Pluto stuff. As it's written here, I'm a lover of Pluto. Like Andreas, I would like to do as much as possible in Pluto. I think it really is something that for me changed the way I was using MATLAB before, then I went to Julia, and then when I found Pluto and the reactivity and the ability to just change something, and while it's recompiling, all the cells are re-executed and just see your results, I think it's a very cool thing. And yeah, basically I also think Pluto is, to some extent, one of the reasons why I was able to push internally in my management to be able to do Julia development inside the space agency. And I did develop some packages that are registered in general. Most of them are Pluto-related stuff. I think the most probably used is Pluto Plotly, which is a Plotly wrapper to optimize for displaying in Pluto. There is this other Pluto Extras, which I think has cool features. I never really announced it. I never really published, so I think a lot of people don't even know it exists or features it has. I will show something in the notebook today coming from this. And then I have other packages and Pluto-related stuff. And you can find this presentation and the thing I'm going to show today on my GitHub on the link there. So if you want and you're interested, you can also check that out. So this is just a brief outline. I will give you an introduction about these two packages that I'm presenting here, which is Pluto Dev Macros and another one which is called the Pluto VS Code Debugger. I will go briefly on why I developed this and give at high level some implementation details. And then I will try to do a live demo of let's say, the highlights of the main features of this, mostly of Pluto Dev Macros, but also a bit of the VS Code Debugger. And then explain a bit of current, let's say, issues or weird things and what I'm planning to do next, mostly to address these problems. So this is a very one slide brief what these two packages do. I think now after Andreas' talk it's a bit clearer to some extent what Pluto Dev Macro does. There were of course I'm a person that is only working on deadline. I'm a deadline-induced panic person. So I'm a hacker. I like to tinker with stuff. And when I knew I was gonna talk for this conference 1 month ago, so I was like, I have a lot of time. I have things that I want to implement. I will try to do this with this package. And in the last months, I completely rewrote the package twice. I did not manage to implement a lot of the things I wanted. I added new stuff, but that's, I think, how life works. So the Pluto Dev Macros, as seen, is a way to import mainly local code inside the Pluto notebook. It tries to streamline this as much as possible without having to fiddling with the package manager and other things. The way I mostly use it is to some extent as a alternative to Revise. To me, it's like Revise with some additional benefits. It allows to automatically import in the notebook scope all of the names of the package you're loading locally. It allows, thanks to Pluto, to redefine structs, which is a very big pain point when in the early stage of development when you're iterating on your types. And then the very nice thing that is, again, thanks to Pluto, is that whenever you reload your code, everything that depends on it is re-executed. And while you're waiting for something, you save your file. And if you don't have very long running stuff, it's nice to be able to just scroll down in the notebook and see what is the impact of the change you just made to your code. And then to help with this again, I also developed this other package because in my work sometimes we have to some extent complex function, and then sometimes we want to debug what is happening when the results are not what we expect. And I always lacked a good debugger. I think this is one of the probably only few things that I think MATLAB still has better than Julia at the moment. I think it's improved a lot. I like it now. But then in Pluto, it was a bit difficult to have some kind of interactive debugging thing outside of putting print or log statements. So at one point, I tried to see if I was able to hook a Pluto notebook inside a VS Code instance to be able to use a debugger. I managed to do it. It was actually much easier than I expected. So shout out to the people doing the VS Code stuff, so that it was very easy to do this. The motivation, a bit, I briefly already talked about this, but as I said, I fell in love with Pluto and I wanted to use it as much as possible for everything I did in Julia. And of course, at the beginning, there are a few things that are not very well suited in Pluto itself to use it for package development. I think I was one of the first people crazy enough to say, okay, I want to create packages with notebooks as files, and started developing Pluto Dev Macro for this. This thing evolved a lot. And now I actually do not use like this in that regard anymore, because I think still that having notebooks as file is to some extent painful, mostly because now that with the package manager, the project and manifest are embedded in the file, it's a Git nightmare every time you update something. But nonetheless, this is still something that is supported by the package. Now I will show you a bit later how I use this more, but I think it's also cool to be able to do what Andreas was showing. It was how I started actually my Pluto journey. And I think it helps a lot with let's say the speed of development at the beginning. It allows you to focus more on changing what you want to change and immediately see what is the impact of what is happening. And then I also use this, again, I wanted to use this as much as possible for our package development, standard Julia package development. And so I always try to support as much as possible everything that the normal Julia package can support, which is like package extensions and other features. And the last point is regarding to the debugger. Of course, as I said, I wanted to be able to use the notebook, but still be able, when needed, to hook into a kind of step in the debugger to see variables and other things. So the main feature that I wanted to have from the Pluto Dev Macro package was, as I said, to work as a replacement for revise, mostly because of the structure definition and the reactivity, with some enhanced feature, of course. There are also some drawbacks with respect to revise, we will probably see, but I think I like a lot where this package is at this stage, and it's helping a lot our internal development. I also wanted to be able to load the package without explicitly having to put all of the dependencies in the notebook. This was the question from Stefan before. This we'll see how it works later, but it's very easy. It's probably not super straight, like the best Julia way to do things, but I think it serves the purpose here, and it makes everything easier. But as it was shown, you have two separate environments: the notebook environment, which is that does not need to contain all of the dependencies of the package environment, which for me was a huge pain when I started this, because I really love the Pluto package manager. You just type using something and it installs it does everything for you. But then when I was at the beginning starting to include other notebooks in my file, they were using different dependencies. I was getting error. I always have to go add all of the dependencies from every other notebook that is included in every other notebook that I'm using. So this was some effort to avoid this problem. Another thing which is a core feature, I think, for, again, development, is that you are able to open a notebook, include the package, and be in the namespace of the module you're developing. So you don't have to explicitly export all of your functions that you want to test to be able to have them like you would have, for example, in Revive. You don't or alternatively, you don't have to prepend the name of the module to the function in order to use it in Pluto. And I think this reduces the friction in the workflow. And as I said, one goal for me was to be able to support as much as possible what is support normally in Julia. So now the package works with package extension. If you have package extension on your local package and then in the notebook you add a dependency that is not on the package, it will trigger the extension of the package. If you have an init function, it's parsed and executed when you load the module in the notebook. Recently I added support for all of this import X as Y, both module names, so that everything is imported correctly in the notebook. Another thing that I recently added, which I think was cool, that is something that Revise does not support, is that you can have include with 2 arguments in your files and use a mapping expression within the local code. This is something I have some tests I added recently. It's probably break with the weird stuff. So if you want to try it, and if there is a problem, please let me know and I will try to fix it. And the last point is more related to what was the workflow show by Andreas, that if you use notebooks as part of your package source, so they are included in your package, and you use Pluto Dev macros inside the notebook will basically, in the notebook, the macro will load everything that is in the package up to the include of the notebook. So you will see it as like if that notebook was a normal file included in Julia. Nothing that is defined after that file is included is in the workspace. Nothing that is defined in the notebook itself is also brought into scope by Pluto Dev macros, because otherwise nothing would work. And so this was at the beginning to mimic as much as possible how the namespace is seen by a Julia file while loading things with include. So the basic usage is like this. Now this syntax is a bit new, but I think it's the thing I use the most now, which is this: you put some notebook anywhere in your package folder that you want to develop, and you did this from parent, which basically extracts the package environment and knows that you want to load this package. And then you just do import asterisk, and it brings into scope everything that is defined inside the package, so that you are able to access all the names and everything without putting the module name in front of it. This will also bring into scope, internally it uses names, but then since up before 1.11 in names, you cannot extract things that were imported by using statements. There is a lot of machinery going inside the package, so that everything is parsed and evaluated, so it tracks everything that is also brought into scope by using and re-put them into your scope in the notebook. This syntax below is before I had this thing that was also tracking using. Basically, for this problem of using, if you had a package that inside was like using benchmark tools, benchmark tool would not be imported in the notebook, and so that was there was this weird syntax to import the dependency of the package you're developing. And the reason why I have this very weird care things, that there is also a way to use normal words for identifying the package. If you see here, there is the package module, which is the root package of the local package. You have parent module, which is only applicable if your notebook is included in your file, and it's basically the module where the file is included. And then this dependency is only like this, but the reason I had this caret is that if you have the Pluto package manager and you have a normal word, you will see the bubble of the cloud saying download this. Even if this inside the macro of course will change everything and will adapt, so it points to different stuff. And instead, if you use this weird symbols, you don't get the bubble, so it was just a shorthand way to achieve what I wanted in the minimum amount of syntax and also avoid the bubble, which is not nicely looking when you see stuff. As you see, you can import things with a different name. You can import just specific names from any of the module. You can also import everything, not because if you just do import asterisk, it will import everything from the package if your notebook is not included in the package, or from the module where the notebook is included if the notebook is included in the package. You can also do this by specifying the module if you want to import everything from another submodule. You can also use relative imports if your notebook is included in the package. So as I said, all of this very complex thing is to try to support as much as possible standard Julia syntax so that it's as seamless as possible to use this for package development. So the same thing will work even when you load your package outside of the Pluto notebook. So some small implementation details. Basically, at high level, what this does, it basically, when you call it, you can call it either something I didn't say here. From parent, automatically extracts the path from where the notebook is located, but you can also give it a specific path. If you have a notebook completely in another place and you want to load a package that is in another part of your system, then you can specify a path. You can also specify a path not just by a string, but a symbol that is defined in the notebook. But there are a few caveats with that approach, so I would go with the string path. And then, so the high level of what happens is you get the project based on the path you provide. To avoid the need of fiddling with the Pluto package manager, basically this adds that project to the load path at the end, so that you are able to load stuff without getting error from Julia. This works without making the package manager complaints, because all of the evaluation of the module happens during the macro compilation, so it does not trigger the Pluto package manager when you load a dependency. It creates a temporary module in the notebook space, and then it basically includes the module file inside the temporary module. It does not directly include, it uses like the expert from Julia interpreter, and it goes through all of it parts the file, it creates the expression and go and cycle through the expression, mostly because of what I said, that I want to track the using statements, and there are a few other caveats that I have to do while processing expression to populate the module. If it finds an init, it runs it, as I was saying. If it finds that there is an extension in the package and that all of the triggering packages are loaded, it will also load the extension code. It will also add a callback so that when other packages are loaded, for example, if you have an extension in your loaded package, but you still do not have the trigger package in the notebook, you can load this from the macro, and when the triggered package is loaded in the notebook, it will then load the extension. As I said, if you do this asterisk, it will import all the names, which I think is the most useful thing when developing. And then lastly, as the last output, it will basically just do some custom HTML and JavaScript so that you get a nice floating button to be able to reload the package easily, and also some stuff to prettify the output, because the temporary module, otherwise you see paths that are very weird. Some very small advanced detail use. So there is a way to avoid getting using statements from the import asterisk, because sometimes you have name clashes. I try as much as possible to limit the internals that I use and the assumption on the internals that I know about Pluto, because this can be problematic, but it needs still to use some internals to do what it does with let's say, as much ease of use as possible for the user. And there are some like situations which are set off by default, but they can be changed if needed. The two main parts, it's possible because, as I said, this package is basically a local module that is populated with the package code. Some things do not work when this is the case, like if you do package version with your package, it will not be a loaded package, so it does not know. If you put this flag to true, then it will register this as a root module. It will specify it to Julia where is its path. It does use internal, so it's a bit risky. I mean, it's not risky, it works, but let's say if you don't want to do it, that's not a default. But in case, for example, you scratch and use the get scratch macro, which requires to know where is the package located to work properly, you might want to put this to true. By default, if the local package does not have a manifest, it will throw an error. But you can also override this so that if it doesn't find a manifest, it calls instantiates in the package environment. And then there is this other flag for verbose printing. But that's a small thing. The Pluto VS Code is very easy. It's just you connect it with the macro that I will show you, and then you can do run or enter like you do in VS Code to enter the debugger. And internally, it just basically calls it sends a call to the VS Code using the JSON or PC protocol. So now let's go for a demo. So for example, this is my package folder. I have this package which is just called simple antenna. I have this test notebook, which is the one I'm showing here, and I have the presentation notebook, which is the one I was using for the presentation. So this notebook will be used to show what happens if you include a notebook in your package. So for example, here, if I just do like this, there is nothing in this notebook, so the only thing that is brought into scope is the name of the package itself. Then, for example, I can go here and do a equals 3 and b equals 5. And you see this button, I can just press it and it reloads. And you see now A is into scope and B is not because it was after the notebook. I can see that A is actually 3. I can change this to 35. I reload. And this, sorry. Better? Then if I do put this inside the module, you will see that now this doesn't work anymore because now what I imported is not the root module, but the module where this file is included. And this works as expected for everything. I will not go into much detail here because we don't have too much time. But what I wanted to show that is nice is, so this is my custom table of content from Pluto Dev Macros where you can hide stuff. So here what I wanted to show is a simple example of one thing which I actually use for work. It's a modeling of a linear phased array antenna. You can here do a struct definition. You can create some of your function to see where to position the elements of the antenna and to compute the pattern of the power in any given direction, which is controlled by, let's say, phased of the various feeds. Here, for example, I put a small plot, and you can see here the beauty of Pluto. When this thing finish precompiling, I will show here. I think the battery is not helping. So now here you see, for example, this plot that I've shown here. The nice thing of Pluto is that while you're developing, you can test what happens when you are increasing, for example, the number of elements, when you change where your antenna is pointing. And then if you go here, which is the notebook that is outside, I can also go here and do like this, and I will have brought into scope the module and the linear array. I can create it with something like this. Then I realize here, for example, I want to be able to specify that the spacing of my elements is not just 0.5, so I can go here and do spacing. Here I will just do, I will get some error here. So now I can get my spacing here. I can show that this can also be changed. But basically the gist is that this tries to simplify as much as possible. You can keep working on your notebook file. You can keep testing. You just do a change here. You reload your package by pressing this button. New things appear that you put in your code. And I think this helps a lot with all of the development.
Thank you, Alberto, for such an insightful talk. Are there are there any talks from the audience?
Thank you so much, Alberto. Same question. Like going to the Visual Studio Code, you have the project.toml. You're
Yeah.
managing this manually then, or is this also
The
somehow
project, yeah, the
included?
project in your local code,
Yeah.
it's like you would do a package. You have to decide which package you want to include and everything. But then once you have the project, you will basically just it will add that to the load path, so that everything that is there, it can be put into scope.
Yeah, thank you so much. Makes sense.
Any more questions?
Hi, thanks for the talk. It was very interesting. I'm just wondering what your feeling is about the fact that this takes package development to a very different place from what most package developers would do. And sorry, I'm over here. Yeah. So, do you feel that though that this is going to do you have the sense that you would develop a package in Pluto and you would always keep the development in Pluto?
No,
Or
so
that you would reach some stage where you say, okay, now I'm happy with it. Now I want to export it as a much more normal Julia package so that if somebody finds a bug, they can just dev the package and send me a patch and they don't have to learn a whole new workflow, in
so
other words.
as I said in the beginning, I don't use Pluto notebooks as package source anymore.
Okay.
What I do is I have a normal package, like so all of the things I showed you here, you could have just done in VS Code, changing code, redefining struct,
Yeah.
and then reloading. The nice thing is that this way I'm able to redefine struct, I'm able to maybe put plots, do extension, and check this very easily in Pluto. But then now every package I do is normal Julia with no notebooks except just for testing, and then with CI and everything. So it's just really a tool for simplifying, let's say, assessing the new changes that you're putting in your package.
Excellent. Thanks.
So once again, thank you, Alberto. An applause for him.
Thank you. And sorry I didn't manage to show the VS Code, but I will send the link.
Really cool stuff. Ready? Good. Good morning. For our next talk, we have two speakers, Patrick and Ronnie. Patrick is currently a PhD student at the University of Delft. His work focuses on trustworthy AI for finance. And Ronnie is an associate professor from the Norwegian University of Science and Technology. He has some really cool packages that we use in our lab, so manup.jl and manifolds.jl. So the stage is yours.
Thank you very much for the kind introduction and for allowing us to speak about something that's not related directly to my packages. I'm just using that, namely Quarto extensions for the Julia community. If you want to see the slides yourself, the QR code down here is the slides on the net already, but we have a link on the last slide as well. So we split our talk into 4 parts. I will first talk a bit about what is Quarto, and then the next 3 ones are what do we use it for. And I'm mainly using it for documentation and tutorials. But let's start with the first part. What is Quarto?
Yeah, then we'll go on to see the...
Oh, wasn't that my part? Go on. Just give me the next slide. Exactly, what is Quarto? So Quarto is an open source cross-platform publishing tool for scientific works, just in very general. It originally comes from, I think, Markdown R or R Markdown. So the idea is you write Markdown code, but that includes code. So we brought a small example here. That's just a header. You have a bit of Markdown code, and then you have Julia code. And here we also already have one thing that's nice. You can say echo true to see results of that code block or not. So you could say echo false, then you just see the code but not the result. Because maybe the result is a very cluttery, long output, like an error message, which is nearly infinitely long. So it's based on Markdown, and for me, if you're coming from Pluto, I originally came from Pluto, the switch is, Pluto is a Julia code file with Markdown strings. This is a Markdown file with Julia code cells. But these are basically code cells that run. And behind that, they also use a lot of pandoc, so you can basically mark down to anything with Quarto as well, so to PDF or something like that. And it's really for technical reports or any documentation you want to do, and renders that into different templates and custom styles. That's the idea. And really easy to write, hopefully, because it's really just Markdown. So the first thing then is Julia themed Quarto.
Yes, thanks, Ronnie. Yeah, so I'll talk a bit about a first set of Quarto extensions. Extensions are essentially just a way to extend the behavior of Quarto. In many cases, you will perhaps want to just extend the styling. So sometimes many of these publishing systems can feel like they're boxing you in a bit into a certain style framework. So the first very simple extension that I'll be presenting here is just Julia-themed styling for your Quarto documents. This is all open source, so you can download it and get started. As you may have noticed, there's already some Julia colors here in the slides. So we're actually using the extension to produce these slides. It's very easy to use extensions in Quarto. Everything is installed just straight from the command line into your existing project. And then you essentially, to use those extensions, just define those options in the YAML header. So the YAML header just specifies essentially the configuration for your current Quarto document. We have added theming for HTML documents, so HTML articles, as well as Reveal.js presentations, which is what you're looking at right now. And then there are very simple Quarto commands for previewing your documents when you're working on them and also ultimately rendering them. So just a bit of detail here on what the theme actually uses. We use the Julia mono font, which is a font that's open sourced for all monospace and code text. Following recommendation from Cormulion, who some of you may know from the online community, I've recently switched to this Barlow font for font headers. And then there's a few other fonts that we use for details. All of this is just a starting place in case you want to have a theme that gets you closer to a Julia style document. But you can go on and then add your own touches to that. So it's, again, not meant to box you into some standardized theme. It's just a way to get you started if you want to. This is what inline code looks like. So this print statement here is using the Julia green, and it is using the Julia mono font. Unfortunately, code cells in Reveal.js are not affected, so this is just the default code, but we can move over here to see on our corresponding website what this looks like. So again, we have a Julia color theme going on here. And let me just move back here. Okay. And in general, we try to use the Julia colors as much as possible. So different callouts are in Julia colors. So it's very gimmicky, but it just, I think, adds a nice touch to your presentation slides. All my talk slides were produced using this extension. Yeah, and now we'll move on to some actual tooling. So how to use Quarto for your documentation.
Exactly. So I was writing a few tutorials for one of my packages, man.jl, and then I had the following problem. I wanted to have them integrated in Documenter, and with that I mean I want to use addref to reference any document string that we have in Documenter available, or even link to other documentations with Documenter interlink from Michael Goertz. Include mathematical formula, of course, so that's really just some math stacks or something. And it should render into Markdown to then be further rendered by the documenter. That was my workflow that I wanted to have. But further on, I also wanted to have that you see codes and results, and that also includes plots. It should be reproducible, so 100% reproducible. We will come to that in the end. And it should run on CI, so it should be hopefully also cached, because if you write 20 tutorials and every time you kind of like publish a new version or you do a pull, it shouldn't run all these 20 things, but maybe just the one that you changed. That's the overall goal that I wanted to achieve. And that turned out to be more complicated than I thought. But let's get into that. So what you do is, so in your package, what I did just to follow up on the next few setups, I have a tutorials folder where I write a tutorial like this. And I just introduced one or two further things like output false means this cell is never printed. So echo false means the result of the cell is not printed. Output false means the cell itself is also not printed. So this package activation is important for us to be reproducible. But if the user reads the tutorial, that's irrelevant. And then just starting a bit of things. But this is basically I cd into the directory tutorials, and I activate the environment to make it reproducible. That was the idea. So I want to run the code when I'm generating the documentation, and it's not yet there, as an MD file to then be further rendered and generated into the menu of the documentation or something like that. So that's the general workflow I wanted to follow. Yes? And then what you have to do is you set up this Quarto YML file in the tutorials folder. And there's one important line here which misses the last slash because our page is a bit too short, but I couldn't shorten that. That says the output directory is the docs source tutorial folder. So as soon as it generates the markdown file, it copies it over there. And then you can even specify, please don't render this file. And that's for, well, you do a benchmark that runs an hour. And that one you check in manually with git add and do not render on CI, and then you exclude it here. That's the idea. So whenever you work on a file, you would do just Quarto render file QMD on terminal, and it would just generate the markdown file. If you specify the folder, it runs everything in the folder besides the one that you exclude. And the rest is just a bit of setup. I want to render to markdown, so I say I want to have comment mark, and please do $ as techmath. So I have to use dollars for techmath. But then it generates all that, and it keeps a cache in tutorials_freeze, so it recognizes was the QMD file changed or not to re-render or not re-render. That's the main technicality here. Then we come to the third workflow slide. I forgot this one. In VS Code, the preview that was already mentioned is automatically available, so you have two tabs. One is your code, one is the markdown preview, and as soon as you save, it renders. It's a bit of LaTeX style-ish, not live preview, but nearly live. Okay. Then the third part is, how do I get that into Documenter? And the one disadvantage of Quarto currently is it renders with Jupyter that needs Python. And you're like, oh, I have to install Python, and I have to remember all the versions, and it has to fit. Luckily, there's conda pkg that does that for us. So we just specify in conda pkg toml that we want to have some Python version and any Jupyter version. And anything that I add to my make.jl, all that I have to add is this one here. So with the environments from conda pkg, I want to do Quarto render the tutorials folder. And that means whenever I call make.jl, it renders all my tutorials. But since I have the freeze folder, only those that were changed. That's the whole setup we need. So that's the whole workflow locally. And the next slide is, I think, the workflow on GitHub Action. The one thing you have to add to your Documenter GitHub Action is these few lines, which is basically a cache. So I'm caching the tutorials freeze folder, and I'm caching the docs source tutorials folder. Because this one stores the readily rendered ones, and this is the freeze where Quarto checks whether it has to re-render, and then we're fine. So with that, the GitHub CI automatically only re-renders those that were changed in the last push compared to the cache. And that's then really neat, and Documenter doesn't run for 2 hours, but really just 10 to 15 minutes again. That's a bit technical and took me a while, but luckily it's now working. So then I hope my next slide is already caveats. Ah yeah, there we are. Caveats are, if we have a breaking version of the package, we have to manually delete the cache on the GitHub CI. Otherwise, it just thinks it's half cached and it doesn't work. So I would say cache is maybe a bit of a trade-off sometimes because breaking changes. Maybe one thing that might help if the last cell of your Quarto notebook is then some print that just does package status so that you get the recent package versions. Also for someone reading the whole thing, because your tutorial might be outdated. And then at least you can see that in the last cell because it says this one ran with, I don't know, manop.jl 3 point something, which is from last year. And then you know, maybe I should ask someone what the new style of that is. The one caveat that I ran into was we want to do add ref to something to reference something. And sometimes this is the format you have, that you have a text, but you want to reference B. And since Quarto thinks those are all URLs back here, it escapes the space. So you always get that one, and that doesn't work with Documenter. The one trick that you can do in Quarto is behind the, you put it in code, so backtick, and then you say this is comment mark, and it stays as is. That's the equal comment mark thing. And then you can use anything in Documenter, ref, or something to reference something. And the only thing that's different from classical Documenter is 2 backticks was math in any Julia doc string. The Pandoc developer is not so happy about that. We have to use $. Well, for Pandoc, anything in backticks is code. And they don't count number of backticks just to have basically nested codes. That's what they do. And I talked to the Pandoc main developer, and he was like, they use what for math in Julia Documenter? So they don't want to support that, and I can completely understand that because counting backticks is a probably quite complicated thing. But with that, with these caveats, you're basically good to go. And just to summarize, I think my next is already my summarize slide for my part here. So as I said, we get tutorials that are reproducible, that have executed code, even plots work and all like that. They are cached and rendered on CI, so you don't have to care about that yourself. It's done automatically on CI. You can use addref from Documenter, and just to repeat those 2 packages, because I'm really a fan of those, you can use Documenter interlinks to reference doc strings from other documentations of other Julia packages. That's Documenter interlinks. And you can use, if you set it up correctly with a bibtex file, Documenter citations and cite really literature. And that's one of the reasons why I wanted to get to Documenter Markdown, to have all that in one place, and even have the literature at the end of the tutorial. The same style as Documenter does anyways with this amazing package, Documenter citations. And again, both are from Michael Gertz. He did some really great work on Documenter recently. So there's the shout out for that. These are clickable links. If we have time in the end, we can maybe take a short look into the ManOpt optimized first example and its source. And the Julia forum post I posted is a long explanation of all the setup that you have to do. But let's continue with the last extension before we get into maybe a bit of demonstration of code. I forgot a slide. Sorry for that. One thing that's coming soon, I mean, I said we need Pluto to run Jupyter to render all that. And it's not like, there is a recent development, which is Quarto Notebook Runner JL, which should eliminate the use for Jupyter and Python in between. So then you have a whole workflow that just uses Julia. And even better, there's an issue open by Fonts already that discusses, instead of Quarto notebooks, we might also just expect Pluto notebooks to work as well. And then I might even switch back to Pluto because that's how I interactively write most of my stuff. And then I convert it to Quarto currently. So that might even be adventurous for that. So we will see. Maybe let's do questions after. Okay. I know that it's out, but it doesn't work so well with my workflow yet. So it's.
Okay, I thought you, because of just a week ago, they posted from pre-release to release.
Yes, the main problem is that every notebook needs the config currently to run with that, and I can't do that in the _QuartoML globally yet. So that's my soon. It's definitely there to try already. It's just not yet 100% working, but I'm really looking forward to that. But with that, I think we're really at the point to get to the last of our extension blocks, right? Yeah.
Show of hands, has anyone here published in JuliaCon proceedings? Oh, okay, I was expecting at least one or two, but fair enough, you should. The process is actually already really good because they use the JOSS, the Journal of Open Source Software, process. So reviewing takes place on GitHub, for example, which I really like. They have a nice Julia package repo that makes a template available. One thing that I was still missing when I was working on my last submission was Quarto support, which is maybe a little much to ask, but I see Luca just joined here. We could actually have this in the future. Wouldn't it be cool if all the documents that you perhaps already produce in Quarto for your documentation, so we just heard a lot about that, if you could use those, which are mostly just pure markdown blended with some code cells, and move chunks of that directly into your JuliaCon proceeding submission to have a nice starting point. To do that, I've worked on a extension. So we saw a very simple extension earlier. Another form of extension that Quarto also supports is extensions for academic journal LaTeX templates and JuliaCon proceedings. So the Quarto JuliaCon proceedings extension is just that. Again, very easy to install this. It's open source, so you can already try this out. You just add the extension locally to your project, and then you specify the configurations in your YAML header. And what you get is ultimately a PDF that looks already very, very, very close to what the final Quarto submission with the official template currently looks like. There are a few discrepancies still. So disclaimer here, this is not yet, officially supported by JuliaCon proceedings, but hopefully, looking at Luca here again, we'll get there in the future. Yeah, so thanks. So the motivation here is that we've heard this already now, that of course it's nice to have both your code, your results, and your text all in one document. Quarto has support for executable code blocks. So there's an extra layer of unit testing, if you want, where your document that will ultimately make or render the publication will also execute code examples that you're running perhaps or showing as part of your JuliaCon proceedings publication. So if anything is wrong there, you will see that in the final render and the code will throw an error. So that's nice. And of course, one key advantage of Quarto is that you can use the same source document to render to different document types. So you can render to PDF if you prefer to print out your readings. You can also produce a HTML document from that very same source document. And we'll see an example of what that could look like in a moment. So this is essentially taking my first JuliaCon publication and putting it through this process and rendering a HTML document instead of a LaTeX or a PDF document, and it looks like this. Yeah, this is just a website. You can see that it uses the Quarto Julia theme. So again, we have the Julia colors here. Of course, this would support animations in your JuliaCon proceedings publication, which is quite nice, I think. Math is, of course, supported. Something like, I think here we used mermaid diagrams. They immediately supported. So just to give you a flavor of where this could go. And then I'll just leave you with this slide. So currently, as I said earlier, there are remaining discrepancies, but they're very minor. So on the left, I think we have, yeah, exactly the proposed version, so rendering my previous publication through the Quarto extension, and on the right is the published version that's currently on JuliaCon proceedings. You can see that there's like minor differences here. I haven't really been able to figure out what's going wrong, but I think it should be possible to get us to the final point where the extension renders the same PDF. Okay, so finally, just a few more resources for you if you want. So there's, of course, the official Quarto documentation. There is Ronnie's amazing Quarto blog post on writing documentation with Quarto. So that's this third bullet point here on ManOp tutorials. Let me see what this one was. Oh yeah, this is a blog post that I have if you just want to know a little bit more about what Quarto extensions are. And then we have a few examples. Yeah. This one, yeah?
Yeah, the last one. Let's see where it votes and make it a bit larger. Just to, where's the plus? Too many different keyboards. I have 3 keyboard layouts in my mind, so I mess it up on every. So one thing you can see here is, this is again a citation. If you would click on that, you get to the references. So these two as well. This remaining manifold link actually links from manop back to manifolds.jl, so that's in Documenta interlink. And if you scroll down a bit, I mean, you see a bit math in there. I'm a mathematician by trade. But if you go a bit further down, you see the first code here where you directly see, I want to work on the sphere. That's again a link to manifolds.jl, not directly the package. And then you see, oh, if we run gradient descent, that's the result we see. So you always see the code and the result. And that's what you automatically get, and you know that it works. And with that, thank you for your attention.
Thank you for showing us this really cool stuff. Are there any questions for the audience?
Thank you. It was a nice talk. More of a maybe a shield. If you also want to do package development in this, I gave a talk on Wednesday on doing literate programming using Markdown, and I think it would be very well possible to combine my package. It's still a Python package, so you do need Python, but it allows you to tangle files from Markdown into what would become a normal package, and it also allows you to do the reverse. So you can do debugging on your code, and it updates the Markdown for you. So then and it has some Quarto syntax support. So in the future, I will try to build in Quarto support in there, and then you can have all of this and package development.
Yeah, thanks for the comment. That sounds very interesting.
Hi, thanks a lot. It seems very cool. I actually never knew about Quarto for real. Just one question. Would this be a suitable way also to write bigger things like book chapters or stuff like this, or is more for smaller papers and or for some reasons?
As far as I'm aware, there are books written in Quarto, definitely. I mean, then you have different markdown files and you would render them individually, but then there's a way to combine that again to one so that you don't have a 20,000 line markdown file. I mean, you then want to organize the stuff a bit, but I think there's quite a few ones.
Yeah, Quarto actually supports quite a few different outputs, so even entire websites. Myself, I'm a bit of a Quarto addict, really. So even my website is built in Quarto. It's also using the Quarto Julia extension, so that's the same font theme here, and then a little bit on top of that. So you can, well, I don't want to make this a product pitch about Quarto, but you can do a lot of things with Quarto. So there's a lot of different outputs here.
Okay, thanks a lot, and very cool and polished it looks.
Yes, thank you for the talk. And to continue a bit on the last question, so once I saw the Quarto talk here at the previous JuliaCon, I immediately switched to it for writing my course notes for my classes, and it's very easy to also write large projects, much easier than LaTeX, I would say. Thanks.
Yeah, I agree. Thanks.
So once again, thank you.
Thank you.
So, welcome back again. Without further ado, let's introduce Julius Kronbickel. So the floor is yours.
Thanks. All right. Yeah, thanks for coming to my talk about summary tables JL, which makes publication-ready tables in docx, HTML, LaTeX, and types. Yeah, I'm Julius, a product engineer at Pumas AI, which you can check out at pumas.ai. And this QR code you probably saw for a couple minutes if you want to check out the slides on your own. So brief outline what I'm going to talk about. Why did we make this this package in the first place? Then I'm going to show some examples of predefined table functions we have in the package and how you can make custom tables. And then a brief look at a companion package called WriteDocx JL, which we also open sourced, which is one of the backend packages for summary tables. Yeah, why did we make it in the first place? So at Pumas AI, which is or partly does consulting for pharmaceutical companies, a lot of tables have to be generated for reports, analyses, and so on. So we needed a good tool for that, but we had certain requirements how these tables need to look. One big one is that we need to merge cells, which in the common format of just having a matrix-like table isn't supported. If you know pretty tables JL, it doesn't do merged cells, for example. And then we needed a bunch of output formats like HTML, LaTeX, docx, and types, but with very specific formatting requirements. So if you use a converter tool like Pandoc or so, it's harder to get to the exact output that you want. It's nicer if you control the output exactly. So we wanted to have our own. And we have no ASCII output because it's hard to do with merged cells, but we don't really need it that much. And then, yeah, we wanted to have this opinionated style, which you might be familiar from LaTeX tables like book tabs. I mean, it's pretty classic, this minimalistic style without vertical lines. And that's sometimes hard to do also in, for example, in docx. That's not so easy to achieve. Right, so some examples, what tables look like. We have the one table is called table 1, which is a typical table to summarize columns from a data set. And here you can see some features, for example, different variables like age, blood type, or whether someone is a smoker being listed in the rows, split out with different analyses, like different summary functions. And then you can also stratify by other categorical variables, and it does some summaries there, how many people you have in each group, and so on. And you can see that the table is not like completely standard. There's some indents going on, some merged headers. Yeah, that's one example. The other is called a listing table, which also has an bit of an unusual layout because you're presenting raw data from like pharmaceutical trials, which you list interleaved with summaries that you do per group, and there's also a convenience interface for that. I'm not going into detail further because I think not many people here might be interested in exactly these functions, but more like in the custom functionality. So that's coming next. I'm going to show just briefly how to do one of these custom tables so you see a bit what the interface is like. So this is the example table, which is like fake data that I made up about trees of 2 different kinds. And let's see how you would build that in this package. So we start with just a vector of strings for the column labels and put that in a matrix. Basically, you can see that it's there's this little apostrophe for making it into a row vector, right? And then call table on it, on this matrix, and then, yeah, that's the first part. Then we can, for these cells, that we wrap the cell type around the values that we actually want to show, and we can give that some options. So here I give it bold, true, and a border. The border can't be seen because it coincides with the table border, but in the next slide you can see that the deciduous and evergreen, they have these little borders on top. And then the next thing is the species, which again is just a vector of strings wrapped in the cell, and we can concatenate that in this matrix, like the classic thing that you would also do with numbers. I mean, everybody's familiar with that. The next thing is some fake data. In this case, just again a matrix of strings. You could also use numbers, and there's some more convenience in summary tables how to handle rounding, for example, how exactly you want to display these numbers. Yeah, you can check out the docs for that. There's a bunch of options. Again, we just vcat that into the table, and now we have already this one. And then the next step, we want to actually merge the column headers. So we, is this not working? Oh yeah, no. So we pass the merge true keyword to the cells that relate to the column headers, and then it will just merge all the ones that are exactly the same next to each other. So that's a pretty simple way to do this, I think. Then you already get the pretty close. The next, well, this thing goes a bit back and forth. Yeah, it jumped, I think, over the labels that I added, and already jumped to the annotation. You can see it highlighted the water consumption thing, which uses one of the internal types of summary tables, which when you pass that, it will automatically do like a footnote with the numbering and so on, and put that in the bottom there. And then the last step was passing header 2 to the table, and then you get the additional line. Because, I mean, in most of the table packages that assume you have a data frame-like thing, it doesn't. It would usually just give you the names and then the header line, but a lot of formats are not really built like that, so here it's completely flexible. You can do it however you want. Same with the footer, which I don't demonstrate here. Yeah, and then let's take a brief look at the write docx package, which is the other one that we open sourced. It writes docx packages with docx files, which are like zipped XML files in the back. And it has types that are very close to the original schema that Microsoft published for this. But there's some convenience sprinkled in. So you can, so it's more easily, a little bit more Julian. But you can do basically anything that the schema allows you to do. And then, yeah, it's verbose, but more powerful than going through a converter, as I said before. You can't currently read into Julia data structures because there are so many tags that I didn't have the time to make the Julia structures for all of them. But yeah, that's how it looks. Here I'm actually pasting one of those tables in, and I don't know, I haven't seen Word tables look like that before, because I think you cannot manually do this in Word, but if you do it programmatically, you can, like with this gap here and stuff. Yeah, so there's some fun. And yeah, I wanted to mention that you can, in principle, splice XML output into existing doc files that you get out of write docx. So it could be pretty flexible to enhance like some workflows where you already have docx files, but you want to change tables and so on. But yeah, we haven't published anything about that yet. But in principle, it's possible without reading into Julia data structures first. You just modify the existing file with the output you get. Yeah, that's it. Thanks.
Thank you. Oh, good.
Well,
Yeah, thanks for showing your package. I was wondering, we have a PowerPoint package which we open sourced, and I was wondering whether you know if there's like a commonality in the XMLs between docx and pptx.
yeah, I mean, they all follow the same basic, the basic
So
format.
we could write a common backend that uses both, I guess.
Yes, I briefly checked the pptx package once. Of course, it has some similarities. It's not directly the same, but yeah, that could,
Okay,
yeah,
cool.
very possible.
Yeah, would be interesting. Yeah.
Yeah.
Thanks.
Any more questions? Okay.
All right. Thank you
Once
so much.
again, thank you. Hi, once again. Please welcome Andreas to the stage.
All right. Good morning again, for those of you who haven't seen me before, and also good morning to the stream. So, welcome to my presentation of Jellyfish, a project of mine to build reproducible documents with Julia and Typest. So, I'm Andreas. I'm a PhD student, and I like Typest very much. And the reason why I do this is it's basically a typesetting system that takes code and turns it into a PDF document. So pretty much like LaTeX, but Typest is fairly new. It was only published last year. It's blazingly fast since it's written in Rust. So it should take me like a couple seconds max to build a document. And also I found it rather easy to learn, especially compared to LaTeX. So as a PhD student, I use Typest to build scientific documents. Besides those slides, they're also built in Typest. And maybe I convince you why this is a good idea, because in Typest you have like this fairly simple syntax, kind of like Markdown even for typical typography, like those titles or emphasis. But at the same time, if you want to do more complex stuff, Typest has like a whole built-in scripting language. So whenever you see this hash or pound symbol, this means that now you're like evaluating some code or some function and not just regular content. So you can use, for example, this image function, give it some file name, and then it will include this image in your document. And then you just head over to the terminal, run the types compile command, and you get your nice PDF. But there are a few things that I find a bit annoying about this workflow. So first thing is, when I import this plot and I maybe generate this from some Maki code or so, like I have no clue what kind of code generated this plot after like a month. Maybe I saved it somewhere, but then I don't know where I saved it. And if I want to change something, I probably have to just start from scratch and make the code again. And then also the more attentive you will have might realize that those are not in fact 4 data points, but only 3 data points in this plot. So this text is wrong. So maybe like I've changed the plot at some point. I forgot to change the text as well. So yeah, this is not ideal. And what I would prefer to do is the following thing. Instead of, for example, calling this image function, I would much rather have the Julia code directly in my types document. Okay, so I would like to have like this magical JL function where I can give like a code block and then just write down the Maki code that produces the plot and then get the result. And then since I've defined now my plot inside my document, I can also use that to actually query for the correct length of my data array, and I'll actually get the correct number. So how would we go about doing this? Pretty much when Typest was published last year, people were like, oh, this is great, but there's one thing we need, which is like shell escape, like in LaTeX. I want to like call the shell command from inside my Typest document. And then the Typest maintainers were like, nope, not going to happen. That's like huge security nightmare. But what you can have is metadata. And metadata means you put this into your Typest source, but it doesn't produce any visible output. Instead, it makes your document queryable. So for example, you can say, well, let's have this metadata of some number or some key value data. And then you attach a label to that. And given that, you can then, in the command line, next to the types compile, there's also types query. You can query your document for this specific label, and it will output some JSON of all this data that you put in there as metadata. And this is pretty helpful because we can use this to extract our code. So let's take this example from the beginning again, where we had like the 3 data points and so on. At this position, just add in some metadata, where you say, well, this is our code that we want to execute, and give it some ID, and also a label. So if we query for this label, we can get all the code that is supposed to be executed. And we can do this in Julia, right? Because in Julia, we can just call the command line, like command line, read it into a string, we get this JSON, deserialize that using, for example, the JSON3 library. And then what we get is like a vector of some dictionaries. We can iterate over this vector, take the code of every item, parse it and evaluate it just using standard Julia stuff, put it into a dictionary, and then in the end just serialize this dictionary again, write it into a file. And now we have a JSON file of all our Julia results. And this again, we can now put into Typest, because Typest has an inbuilt JSON reading function. You can read this file, and then again, in our example where we have put this metadata for the code, we can put one additional line that now reads the output at this specific ID that we've given before. And then let's say there's some function that displays the output and handles like images and text and so on. So, and the nice thing, so this is how you would do this in principle, but of course it's a bit messy maybe, and you don't want to do this all the time yourself. So this is why I built Jellyfish, like JL, like as in the Julia suffix. And you use it in the following way. So you just use it, like import it as a types package. By the way, nice thing in types, you always give the version names when loading packages. I think it's a very sensible idea. And then you also tell it, well, in this JSON file, maybe report Jellyfish, there's, here you can find all the output data that you're supposed to, like, of the run Julia code. And then you actually have just this magical JL function where you say, well, this is my Julia code. Please run this and put the result in my document. And then there's the types Jellyfish Julia package that you can just load from the standard, from standard registry. And it's more like of an app like a package. So like Pluto, you just load it and like run one function, like this compile function on your document. And then you actually get the result as a PDF. So here's the one slide pitch. Why should you use Jellyfish? I mean, we have heard about Quarto before, right? And maybe you're wondering now, why shouldn't I just use Quarto? And if you have like Julia code and want to put it to a document, then probably just use Quarto or Pluto. But if your premise is, I want to use types. I like types. I want to build my document in types. But then additionally, I want to add in some Julia. Then this is maybe for you. You can embed images and text and also some types code. So for example, summary tables that we've just seen just works flawlessly. Just call the table1 function and you have the table in there. There's some dependency handling and also other nice features. So try it out. It's on GitHub. And also if you have like any ideas how to improve this and so on, or any other inspiration, just get in touch. Thank you very much.
We have time just for one question. Anyone from the audience?
Hi. So first of all, great talk, really interesting package. I'm wondering, is there any way to communicate back and forth between the types and Julia documents? So for example, let's say I want some specific figure size, right? And I encode that in types somehow. Is it possible to pick up that figure size and tell Julia that you want this figure size, and then from there, the Julia end can sort of figure this out?
Yeah. So I mean, communication from Julia to types works pretty good. If you want to go from types to Julia, where's this slide with the code? Then you would have, like, you can just put it in this code here, right, that you write here. If you have it as some kind of, like, generic types data, there's currently no good way to put this into a Julia, but I also thought of this, so this would probably be nicer, like interpolating this into the code or so, yeah. That's the feature I'm thinking about.
Once again, thank you, Andreas. A big applause.
Thank you very much.
My name's Randall Boys, and I'm going to be talking to you about a package that I've been working on called tidier plots. Just who am I first? I'm an epidemiologist by training from Canada. I work for a company called Presage Group. We work with airlines doing analytics mostly. I mentioned my dogs in my bio, so I thought I'd better show you pictures of them. These are the three of them here. Just in case anyone is not an R user, the tidyverse is the inspiration for this set of packages that tidier plots belongs to. I would say it's the best, maybe the only reason to still consider using R over Julia. It's a comprehensive, connected set of packages that you can use for importing, changing, wrangling, visualizing your data. And tidier.jl, the overall set of Julia packages that this belongs to, is trying to be a drop-in replacement for that set of R packages that's written completely in Julia. So far, I haven't written all these, but the group has written replacements for dplyr and tidyr, which are for rectangling and modifying your data, tidier files to read in data, tidier DB to translate your code into database queries, string manipulation and tidier strings, categorical data handling with tidier cats, natural language processing, and we've got more coming. So there's a lot to talk about. I'm just going to focus in on tidier plots, which is the Julia re-implementation of ggplot. ggplot is part of the tidyverse in a way, but it's also sort of its own little thing. It was written before a lot of the other packages that became the tidyverse, and it's a little bit self-contained. It's its own language for data visualization based on the grammar of graphics. If you're not familiar with what that kind of looks like, this is our code up here. We call our ggplot function. We feed it data, a mapping of aesthetics from the columns in our data frame to the features of the plot that we want to represent the data with. Feed it a geom, and we get a plot that looks something like this. And you can build up plots by adding more and more elements to your ggplot. You add on geom line here, and I get lines that connect to my points. You can add basically anything to build up your plot. So here you add a theme, and it changes the whole look of the plot. That's the general idea of how ggplot works. And importantly, it kind of handles a lot of the defaults for you. You can see the lines picked up that the color should be a grouping aesthetic, and so it kind of handles a lot of this stuff kind of in the background for you. And if you pass your aesthetic mapping to the ggplot, then that translates all into your various geoms, your various mapping. So it's kind of nice to work with. And I thought to myself, how hard can this be to write this in Julia? And so I want to walk you through my first pass at implementing it. At my very first working product that did something that resembled ggplot. It's about 100 lines of Julia. Basically, I defined a couple structs, the ggplot overall, and a geom struct to hold kind of the pieces that we needed. You define what it means to add a ggplot to a geom. Basically, we'll take all of those geoms and just ram them inside the ggplot. Wrote something to pull out the pieces that people had specified inside an AES call, the aesthetics, and outside the AES call, so the arguments or the options, shall we say, to ggplot. Couple of macros that took those expressions and made the geom objects. uh, a function that converted geomes into layers. So these are algebra of graphics layers. Basically just going through all of the pieces that were in the ggplot and multiplying them in one at a time to make an algebra of graphics layer. And then a little bit of logic to inherit from our ggplot into our geomes if the geomes didn't have anything specified. That's it, and it works. So you get something that looks quite a lot like ggplot here, right? You have our macro ggplot arguments that look a lot like how the ggplot syntax works, and the ability to add our plots and add geom point, add to geom smooth, pass arguments, everything that kind of forms the basis of our plot just kind of comes out for free with those 100 or so lines of Julia code. So taking this initial success, I was very excited. I was like, wow, that's so simple. How this is going to be easy. It was less easy than I thought, but we've taken that general structure and dropped I realized I didn't really need them to be macros. I added a lot more geomes, and I added a lot more options and such, but we now have essentially a working copy of ggplot that looks almost identical to the R ggplot syntax. The only exception being you got to use symbols when you refer to columns, which honestly, maybe I'm biased since I wrote the package, but I think it's better. It's new and improved ggplot. So that structure that I had, those 100 lines of ggplot, or 100 lines of Julia code, that's essentially still how the package works, just with a lot of extra conditionals on it. It's still just a set of structs corresponding to the ggplot concepts. It's functions that look like the ggplot functions that generate those structs, definitions for the operators. And instead of translating it into algebra of graphics, I'd now go directly to the Mackey's spec API.
So, Randall, sorry to interrupt you. We will have to cut it here.
Oh, sorry.
And maybe, apologies for that. If you have any questions, you can reach him afterwards.
Sorry. OK, so this is what it looks like. It's got all the options. You can generate a plot that looks like this. Thanks.
So let's welcome Simon and Julius to the stage.
Okay, yeah, welcome. This is our talk about what's new with Markey, what happened in the last year. Let's dive in. So the first thing is the community has been growing, like usage of Markey has been going up. We see that in the number of issues, the number of pull requests, the number of stars on the GitHub repo, the number of readers in the docs, the gap there being the new docs. And yeah, so things are looking good. The citations, I'm very happy to see the things that people are doing with Markey. This is just some random papers that have come in the last couple of weeks that looked nice, where people have been using some features of Markey. And you can see the citation graph, and really a lot of people are using this now to generate real results, which makes me really happy, or us really happy. Yeah, so let's see what the developments actually were in the last year that stood out. So yeah, we have new docs now using the Documenter readpress generator, which is nice because it's really not a good use of our time to write HTML code, I think, as we had to do before. And so now we have this nice system. I think it's much more usable and better to search than it was before. Then new is the plot attribute validation. So we finally fixed this problem that keyword arguments that were wrong were silently swallowed by Markey. So now you get nicer errors that point you to like what's going on and reminds you what the options are that you have. So I think this overall will probably save a couple 10,000 hours or so of scientist time. Right, then we have high DPI support. So there was this problem that GL Markey could only generate pixels at a density of 1, basically, like 1 per pix per unit, or how we call it. And this was bad on macOS with a high resolution screen, and it was also bad on low resolution screens. So nicely, we have now the ability to scale the displays to the screens that they are displayed on. And you can also much better generate high quality bitmaps with GL Markey now that you can use in journals when you want, I don't know, 600 DPI or 1,000 or whatever. So that all works now. Then we made a data shader module after the nice talk by the data shader guy at the JuliaCon last year. Well, never ask again. Sorry, do you even see this? Oh, okay. There was some pop-up on my screen. Yeah, so data shader is nice if you want to interactively look at very large point clouds that are dynamically aggregated into heat maps. And you can see it's smooth for millions of points. It's a bit janky for billions of points, but I think that's still okay. And there's probably still optimization potential there. So if you're motivated, you can dive into the source and help us out. And with that, I'll give to
Hey. I will be presenting quite a few changes that come from me and Frederick, actually. So for one big issue was that we're converting everything to float32 in the backend, because I thought it was a good idea back in the days, because everything needs to run on the GPU. You're doing graphics, so you don't need a high precision for that. But yeah, people have been complaining that if you just put float64 in the plot and actually need the precision, you will get a faulty plot without any error. And Frederick, with a lot of work, fixed this now, and we're internally normalizing the data based on the zoom. So this works now. I spent a lot of time on making access converts for categorical support, because they kind of need to be saving global state in the access to add new categories or to normalize with the dates. And because this is really went into the internals, it was quite a refactor. Frederick added quite a lot of nice lighting support to GL Markey, which you can see there. So now you can have multiple lights with new and better defaults, and cleaned up the whole kind of lighting thing. And also, Frederick introduced some new voxel plot type, where you can
plot billions of little cubes that can be used for some serious big data data visualizations or for some games, I guess, like Minecraft. And we finally have line styles in WebGL Marquee, which was a big missing thing, and also caps and joins. Okay, oh damn. And future developments. So one of the biggest things I want for the future in Marquee is stable funding. So I can actually sleep at night. And I'm kind of all in with Marquee by now. So I really want to grow it. I really want to work on it. And I want more people to work on it. And I can already half announce that we got some nice funding possibly coming in, which will also help us employ Frederick. And we will be able to concentrate on finally improving documentations, testings, and make everything more stable. And a project to improve WebGL Marquee.
Okay, and I think time's up, so I'll just show the image of the Aldraff graphics PR. You can think about yourself.
Thank you. Are there any questions? Okay, so thank you once again. A big round of applause. Simon, the floor is yours.
Thank you. I will be talking about Bonito today, which was formerly known as JSurf. And I built it back in the day to make a web backend for Marquee. And at that point in time, there wasn't really a web framework that had all the support I needed and the speed actually to do all the data transfers, because I always wanted Marquee to be fast. So obviously, I wanted the web backend to be fast as well. It's pretty much a bridge between Julia and JavaScript, using WebSockets to communicate, and I tried to make the protocol really fast, so that you can bring Julia values via observables into JavaScript and communicate it with it. It also allows you to generate normal HTML and CSS via hyperscript.jl. And I added a small and composable widget library to it so that people can start building stuff on top of it and exchange components and widgets. The basic component is quite simple and very similar to what you would expect in in HTML with CSS, just with a bit of a different syntax, but all the keywords are just directly translated to CSS and HTML. So if you want to make like a simple little card with rounded buttons, rounded edges, you can do it like this. And the whole presentation is actually done in Bonito. And this is like an interactive markdown component where the Julia blocks are parsed and done in an editor. So you can actually edit this here and re-evaluate it. Another way to actually create HTML in Bonito is that you can overload this JS render function for your own types, and then you can just basically return the same kind of HTML and CSS mixture in there to actually render types in the tree, in the HTML tree. And this composes really nicely because you can actually get CSS or other dependencies in there, and it will be correctly and only one time inserted into the whole HTML document. You can also bring in external dependencies that already exist, so I tried to keep this very unopinionated, and you can just bring whatever you want in there and then communicate with the JavaScript front end. Bonito already has a few widgets that you can use and build dashboards with. They're based on observables, so whenever you click here on a button, an observable will, on the Julia side, say, hey, I got a new value, and then you can do stuff with that. And you can also put observables into the HTML tree, and they will then update dynamically the HTML. And how you deploy it is relatively simple. You just create a server. You might need to change the proxy URL if it's behind a DNS. And then you just create this app, and in there you just return this HTML tree that you've seen before, where you can insert Julia objects and observables. And then you can add it as a root to the server. And I quickly wanted to show this in real time, basically. So this is a shell into my server, which is standing in Germany. And I kind of hope it's still connected. So this one is running behind Nginx. I already set it up to be mapping this demo.marky.org to the port, to whatever runs on the port 8085. And just to get a quick look, this is how the Nginx config looks for this, so pretty simple. And then we should be able to actually visit this. Oh, it's still the old one. Okay, live demos.
They changed the port.
Oh, yeah. That means I need to kill it. What's the time? I think we still have a bit of time. Okay, anyways, but that was the second example here that I ran before, so you can simply now access it here. I did a small little demo app before JuliaCon to show off some new components and prototype them for using an AI, because I kind of want to make a chatbot for myself to use. So this was a nice little project. I tried to make the app itself pretty short, so that you can just use these basic components to have a text input, to have a drop-down to select a model, and then you just add messages to this grid. and put it all together using these components. And when I start this, it should be somewhere here. Let's use this model here. And this returns also this interactive markdown. So we can edit and eval it and get a Markey plot in here. So that's like how it's composable, that you can just call into this. I also wrapped via OpenAI.jl the Dolly thing. This takes a bit longer. But yeah, that's how you, in I don't know, it was like 70 lines of code or something like that. You can make something relatively complex like the Shed app, which is fully interactive and stuff.
Really cool stuff, Simon. I think I will use this in the afternoon. I will try. A big round of applause. Are there any questions? Everyone is hungry already? No? Okay. Oh, yes.
Thanks. This looks very cool. I wanted to ask, how does this work with the Pluto? Because I remember there were some issues with reactivity, with the fact that you use a separate WebSocket. Is there any plan? I think you had a plan to make it work better with Pluto.
Yes, there's a plan for that, but it's slow moving because I and Fons need to find time to work together, and we have very different schedules and priorities. But we have a way to do this and use the same WebSocket and make it better integrated.
Okay, thanks.
Yeah. But it already works with Pluto. It's just a bit, you need to set up the WebSocket connection separately, which might be a bit more complicated.
So, once again, thank you.
Thank you.
everyone. Welcome to Julia conference. My name is Luna, and I'm honored to be moderator for this session. Let's please welcome to our first speaker, Mr. Alexander Liang.
Thanks for everyone for being here. Today I'm going to present a topic on motion planning optimization. So the talk I'm going to be giving is based off a previous JuliaCon in 2020 on conic optimization in Julia and Jump. So this is an alternative approach to motion planning using optimization-based methods. So some of the challenges with existing methods you may know include grid-based methods. These don't necessarily produce smooth trajectories or optimal trajectories. Sampling-based methods are typically computationally expensive. And here is another approach that may be promising to these issues. So using MICP techniques or mixed integer conic programming techniques is what we're going to show here. So just a brief recap of what an optimization problem is. So there's several things that define it. One is an objective function or a cost function. And that's a function that we want to minimize or maximize. So think of the smoothness of a trajectory or the cost associated with executing that trajectory. Then we define a set of constraints. So using equalities or inequalities. And these sets of constraints must be satisfied. And if any one constraint isn't satisfied, then the problem is immediately infeasible. So some good functions for optimization problems in general are convex or affine, and the reason for this is that it is easy to solve such problems. One of the things that convex problem functions give you is that if you any optima that you find that is local will also be global. So think of a bowl shape type function. So if you start from any part of that function and go downwards to the minimum point, you will always find that point. And probably something to take away from this is that optimization is typically hard because some of the challenges is just trying to pose the right problem to solve. Sometimes we want to solve for many things, but it's impossible to solve for everything. Sometimes the constraints are too tight, and we just got to relax those constraints a bit. And it's sort of an art in itself because we're always trying to find better ways of optimizing the problem. And that could involve better solvers or basically reformulating the problem. So here's a picture of what trajectory optimization might look like. So in 2D, you can see some black dots here. So that is a trajectory, and the colored spaces are basically regions in space that an object like a car or a plane or whatever it is can go through. Areas that are outside those regions are you can call obstacles. What we're going to do is we're going to represent this obstacle using polynomials, and the mixed integer aspect of it is we're going to define these multiple different safe regions. So it's a bit hard to see here, but you can basically see one safe region and overlapping with another. And yeah, that's basically it. So one of the other things that this picture shows you is there's a blue one and a green one. And that is just showing that if your safe regions are not generous enough, you may not be able to necessarily find a feasible trajectory. So one way of doing that is just to increase or decrease the size as necessary. In 3D, the extension of this optimization problem is pretty trivial. Using makey.jl, I've rendered some graphs, and the yellow boxes here are basically the safe regions, and you can faintly see a trajectory sort of going around the safe region from some starting position to an end position. If you look closely enough, you should be able to see that it never gets outside the colored regions, and that's exactly what we want to show. This other one visualization at the bottom here is just basically showing the obstacles in a different color. The output you would see when you're solving an optimization problem might look like something like this, and this console output would tell you how the optimizer is solving that problem. So it'll give you statistics like how many iterations, how long it's spending in each iteration, so on and so forth, and that would tell you how you might want to measure the performance of this formulation, this problem. So you can see that here's another way of visualizing a trajectory. So a trajectory is made up of different segments. So you can see one segment here, and the start of another segment here, and then finally the third segment here. And you can see that each segment is allocated to a particular region in space. Some of the shadings are darker than others, and that's just to illustrate that these regions overlap. So the mixed integer aspect of this problem is basically given a number of segments, how would you allocate those segments to different safe regions? And once you've got that allocation right, then you get the trajectory from your start position to end position. So other than that, you just let the optimizer run, and it should come up with the solution automatically. So here are some preliminary results that I've got. So this was using a package called, a few packages, Purito, Hypatia, and Mosaic. So Purito, Hypatia are Julia packages, and they're to solve the conic part of the optimization problem. The package Mosaic is to solve the, using the outer approximation algorithm, the mixed integer part of the problem. You can see here that as you vary the number of trajectory segments, the blue line, so we've got two different trajectories from two different start and end positions, and you can see the what that looks like with 4 segments, 5 segments, and so forth. You can see that in general, the solve time increases as you add more segments, but that isn't necessarily the case here for 6 segments with this trajectory one. So sometimes it ends up being faster with more or less segments. Okay, so another solver that you could use is the high solver. This is one that I've tried, but wasn't able to get reliable results. So for anyone that can extend this work, it would be great to make it work with highs, because it's basically an open source solver. Okay, so other things that one may want to try is warm start. So if we're looking to make this go a bit faster, you might want to, if you've solved the problem once, then you can solve a similar problem with a slightly different initial position and start position. What we see in the results here is that without a warm start, we don't do particularly well, and with a warm start, we save a bit of time. So if you, as long as the problem is as quite similar to the previous problem that you already solved, then you may see some performance benefits in terms of compute time. So other things, if you're using jump and specific to the solver that you're using, you can also optimize with different parameters as well. So here I'm taking the highest optimizer and specifying the model with its with the solvers that I'm using, and you can see the parameters that I'm using for this outer approximation solver. So these parameters, so it's basically a pi-module solver here, and I'm basically fiddling with the number of iterations, the feasibility constraint tolerances, and basically trying to see how I can make this go faster. And obviously, you may not want to do this, but this just illustrates how you interact with that particular optimizer. We get some sort of interesting results. You can see that if we prematurely stop the optimizer, it wouldn't give as good of a solution. And you can see some of these points here are sort of closer than they need to be to each other. So we pay a price for making that trade-off. And so I just basically the take-home message is we just need solvers that we can control how they optimize the problem. So so this output here shows what we want to see. We can see that we want these numbers to be as close to 0 as possible and meet the infeasibility constraints. Obviously, we want number of iterations to be as low as possible. And most importantly, we want to see that it's arrived at an optimal solution. So from this output, you can collate the results and then graph it to show how that changes over time. One of the things when you're using mixed integer techniques, so here I'm using what's called a big M method, and this big M method is a set of constraints that you add to determine how you assign the trajectories to each other. So a good rule of thumb around picking those numbers is just to select the edges of the map of the set of obstacles that you're in. So the way it's implemented, so basically this is what the code looks like. We're minimizing the trajectory jerk, which is the derivative of the acceleration in time. So what that is basically the smoothness of the trajectory using polynomials. And in this instance, we are using box constraints. Here we set the initial conditions, so we're setting the initial position and the final position. We're also setting the initial velocity, final velocity, and acceleration. Over here are the box constraints, and this is using this big M notation. This part here, SOS, stands for sum of squares. So we take a polynomial, we square it, and what that gives us is a polynomial space, and that is a convex cone. So it's not. So basically, we need to do that in order to make the problem convex. This ZIR is basically making sure that we enforce the mutual exclusiveness of assigning trajectories to safe regions. And that's basically can take only values 0 or 1, and that is the n by r data structure. Okay, so these are the constraints here, are the stitching conditions. So basically, to create a trajectory from segments, we have to stitch the end of one trajectory to the start of the next trajectory. And so we do this for the position, the velocity, the acceleration in 3D space, so for X, Y, and Z. So that works for box constraints, but we don't just want to represent safe regions as just boxes. So for arbitrary shapes, we can approximate that using polyhedrals. So to create a polyhedral, all we do is just define a set of half spaces, and those half spaces are basically in this form. So AX less than or equal to B or greater or equal to B defines a half space. So equality gives you the hyperplane, and then the half space is basically everything above or below that hyperplane. So another way to sort of show that as a set of equations is here, and this shows also the use of the big M notation. The only thing that changes here, if you're using half spaces instead of box constraints, what you can do to represent this is to define the data structure half space. You got a set of coefficients, x, y, and z, and c, and the inequality to represent the direction of that space. And so by varying x, y, and z, you get different shapes. So the half space is sort of going off in different directions. And when you put that together, then you get a polyhedron. Okay, so some further work. We need to extend to include, well, this has already been done. Want to make this go faster. This is actually pretty slow, so I'll do a demo of what this looks like. But obviously, you want to take advantage of parallelism, and so there's work that's going on to come up with other solvers that use CUDA, for example. So this is a paper from University of Chicago, looking at primal dual methods for GPUs. Other things that I want to look at is possible reformulations of this problem, extending it to solve for jounce, for example, or the fourth derivative of position. So that doesn't currently work at the moment with Mosaic. Extending it to different solvers. So maybe not everybody has a Mosaic license. They might want to use a different solver, and that's fine too. One of the good things about this little project is basically everything is synthetically generated. So the maps and everything you don't need necessarily real world data, but although that may be nice, but that isn't necessary to gauge performance, because you can always add obstacles or trajectory segments and make the model as complex as it needs to be to measure the performance. Other things is just looking at different optimizers and what can be done with them, because what can be done to make things go faster. And to resolve some numerical instability issues. So one of the things that I ran into challenges with is just things blowing up in size when you look at the matrix, for example, and that results in infeasibility issues. So just to wrap up, I'll go and show a demonstration. And we might need to wait a bit, but it shouldn't take that long, actually. So I've posted on GitHub this Pluto notebook, and what that gives you is basically what we've gone through, and you can play with this yourself by trying different optimizers and changing the constraints, playing with boxes, and just getting a feel for what this problem is about. And I think this is an interesting problem because you're going to see it in motion planning for robotics, for autonomous vehicles, for UAVs, they're all trying to solve the problem of getting from point A to point B and finding the best possible trajectory. The other thing that I like about using the optimization approach is because you're just able to embed a lot of these different constraints in just in this sort of way. But one of the things that I probably see that may be an issue with this is it's probably not suitable for real-time applications yet because you need to throw in a mosaic solver into an embedded system, and I don't think that's going to happen soon. So let me know if you find issues. Just raise the issue on GitHub if you do. And you've got the usual communication channels like discourse or email. And I'll look into any issues you may find with the use of this implementation. So it's almost done. You can see it didn't take a long time to pre-compile. So any questions? So this is using polyhedral constraints. So I've commented out a few lines here. You can see if you define half spaces to represent box constraints, you would need a lot of to define a lot of half spaces for the different polyhedrals. But obviously you can generate that, so that's a non-issue. So I'll just show how easy it is to use box constraints instead. So I'll just comment, uncomment out several different lines. And if we let this run again, you'll see the trajectory. So that's what it looks like with wireframes. Okay, so that's all for the talk. Thanks.
And once again, thank you for the introduction and also for the opportunity to present our package here. This is Sasha Stuttgart, and my name is Sherman Panya, and we are here to present our package JuliaCon SurfX, which allows us to explore the properties of polyhedra and their incidence structure, which we also call polygonal complexes. So in this talk, we're going to give you a brief overview of the research we are conducting and how this package helps us to conduct this research. So I want to start this talk by giving some examples of polyhedra, or the structures that we call polyhedra. So in the classical sense, polyhedra are defined as convex, three-dimensional bodies whose surfaces consist of vertices, edges, and planar polygonal faces. But we loosen up this definition and also consider structures that are not convex as polyhedra, and also structures that have a boundary, which are open, as you can see in this picture. And by giving the vertices, edges, and faces names and describing their incidence structure, we can all describe them as polyhedral complexes or polygonal complexes. So on the one side, we have this purely combinatoric, like this abstract description of this polyhedra, and on the other side, we have this geometric description. If we purely look at the combinatorics and look at the polygonal complexes, we view them as lists of vertices, lists of edges, lists of faces that satisfy certain conditions, such as the edge condition, which means that every edge is incident to at least one face, and it makes two faces, and the umbrella condition, meaning that if you look at the vertices and at the faces that are incident to a certain vertex, they can all be arranged in an umbrella-like shape. And if our list of faces has an n-element face, we call it a polygonal complex or polyhedral complex. And if all the faces are three-element faces, we call it a simple surface. So with this, we can also look at the geometric meaning or view of our polyhedra, which is the polyhedral complex, which describes the incidences, and a coordinate matrix, which lives in R to the D times the number of vertices, where D is in most of the cases set to 3, because we look at embeddings or polyhedra in the three-dimensional space. Yeah. So why did we choose Julia to come up with this package and to solve our problems? And there are mainly 3 reasons. The first one, it is fast, meaning that it's fast in code execution and also easy to use. This was really important to us. Then also that the mathematical and scientific community is shifting towards Julia, because there's a lot of functionality which can be employed to conduct research. And also there are a lot of packages which you can employ and use for the daily business.
Okay, so let's look at an example on how to use our package. Let's say we want to construct a cube. And as Raymond said, in our view, combinatorics come first. So as opposed to the talk we just heard about other polygons or polyhedra, it's not enough to supply the coordinates and just take the convex hull over those, but we have to actually supply the combinatorics of our polyhedron by giving a list of faces. In this case, we tell our program, okay, look at this polyhedron, and you know the faces consist of the first, second, third, and fourth vertex, 8, 7, 6, 5, and so on. On the other hand, we have to give the vertex position. This is, in this case, a 3 by 6 matrix, or 3 by 8 matrix. Every column corresponds to one vertex and contains in it the coordinates of it. And as you can see, if we invoke our object here and call this the cube, then we get returned a polyhedron which is embedded into R3, consisting of 8 vertices, 12 edges, and 6 facets. And this struct saves the vertices as this matrix and edges and faces as a list of lists. Okay, as we want to conduct research with it and publish papers, we also have to have a plotting capability to allow us to look at some plots. On the other hand, it's almost always easier to work with those polyhedra if you have a picture in your mind how they look. So we implemented a way to plot our polyhedra we construct. This is powered by Plotly.js, and they are three-dimensional interactive plots. We have the possibility to change the face colors, add edge labels, and so forth. So we can really have a diverse range of what pictures we can create and publish. But obviously we want to get information out of our package. We want to know something about the structure. And one thing we can ask ourselves, okay, if we have this cube, then what are the face adjacencies? This can be calculated by invoking this function, facet adjacency of cube, and this returns an adjacency matrix of the different faces, where two faces are called adjacent if they share a common edge. To do this more efficiently, we actually implemented a half-edge data structure. This means we take every edge and divide it into two directed edges, one facing in one direction and the other facing the other direction. And then we can associate to each one of those two half edges one face, which is adjacent to the original edge, and this allows for a very efficient iteration through the incident structure of our polyhedra. On the other hand, we can ask, okay, what are the incident edges of a given face? In this case, in the upper picture, when we give the cube and ask what are the incident edges of the face 1, 2, 3, 4, we get 4 elements. As you can see, for example, the first edge, which is listed there, it is set to be 2, 1. But when we look at the face above, you would guess that the first edge would be 1, 2. But this is because we actually return the edges as a subset of the edge list, which is stored in the object itself, and not just look at the input, in this case, this list 1, 2, 3, 4. And we can ask the opposite question, given the edge 1, 2, what are the adjacent facets in our cube? And we get exactly 2, luckily. And it is the faces 1, 2, 3, 4 and 5, 6, 2, 1. Note, by the way, that it is no coincidence that in one of the faces 1, 2 is appearing in this order, and in the other face we have the order 2, 1. This is because when we construct our cube, when we construct the object, an orientation is calculated so that we can actually calculate this half-edge data structure, because for this an orientation is very important.
So as we try to indicate, there are a lot of interesting problems and interesting properties you can compute and observe in polyhedral complexes. And in order to exemplify this more, we are going to list some of these problems and go into more detail into one problem and show how this package helped us to solve our problem, which we were looking at. So if we just look at the combinatorial properties of our polyhedron, one might ask questions about the incident structure, meaning like on the right-hand side of the slide, we can see the incident structure of the octahedron, the Platonic solid with 8 triangular faces, and we, as I described at the beginning, we give the vertices, edges, and faces some names, and we could ask, okay, what are the faces which are incident to the vertex 1? And then our function would say, our package would give us the answer, okay, the faces are 1, 3, 5, and 7, hopefully. We could also look at symmetries of given polyhedra and see in what way do the symmetries give us properties or ideas of how our structure looks like. And we can also look at edge colorings. So on the right-hand side, you can see the incident structure of the tetrahedron. And you can see edges colored in 3 different colors, which is also called a Greenborn coloring, just to name the term. And although these colorings are purely combinatoric, they have a geometric meaning that different edge colors correspond to different edge lengths in the polyhedron. If we look at the geometrical properties, one might ask questions about the rigidity properties, meaning that if we look at the polyhedron and forget the structure of the faces, can we introduce movements to the vertices so that edge lengths are preserved, but the whole structure moves a bit. So on the right-hand side of the slide, you can see the famous Picard octahedron, which is from the incident structure the same as the regular octahedron we saw at the beginning, But in this case, you can see that there's a flex, whereas the convex one we saw at the beginning is rigid. Another problem that we are interested in is the embedding problem, meaning that if we look at the incidence structure and forget for 1 minute that we took the incidence structure from the polyhedron, is it possible to embed this incidence structure into the three-dimensional space with given edge lengths? So, and it is possible, and in some cases there are more than one solutions to this described problem. And the last one, where we're going to go in much more detail in the following, is interlocking properties of assemblies of polyhedra, meaning that we have a set of blocks that are kinematically constrained by a frame. So, and this is the example where we are going to more detail, and I'm going to show you how the package, how functions of our package work. So in order to tell you what a topological interlocking assembly is, I'm going to start with a non-example of a topological interlocking assembly. And let us assume that we are given this set of cubes that are assembled in the three-dimensional space. And we see that we have two different types of cubes, the red ones and the gray ones. And let us assume that the red ones are glued together and fixed in space. If we do that, then I hope it's easy to see that the gray ones can be moved out of this assembly by just moving them straight upwards. But there is a way to assemble cubes so that this movement is not possible. And this is what you can see here. So if we assemble cubes in this manner, fix the red ones in space and glue them together, it is not possible to move the gray ones out of this assembly. And such an assembly is what we call a topological interlocking assembly. And in literature, there are a lot of different examples of assemblies, and there's a lot of different work. So if you want to get an overview, I would recommend to read the work of Diskin, Esrian, and Pasternak. They have done fundamental and extensive work on the study of topological interlocking assemblies. And we are, in particular, are interested in the construction of those assemblies and also in the proof that a given assembly is indeed a topological interlocking assembly. And we have brought some examples for you. So as you can see here, there is an assembly of blocks, and we printed a frame in green. And we want to stress that there's no binder, no glue. The whole structure is just held together by the block geometry and the definition of the frame. And we have some other examples. A football, which is also really stable, just held together by the block geometry and no addition of binder or any additional material. Yeah, so I'm going to show this in a minute. One idea which we are pursuing in the construction of these interlocking assemblies is that we start from tilings of the Euclidean plane and try to grow them into blocks that might have this interlocking property. And one tiling where we used this was the Einstein tiling, or more rather the Einstein tile, where the copies of this tile can be used to tile the Euclidean plane. What is the Einstein tile? The Einstein tile is the answer to the Einstein problem. What is the Einstein problem? It asks whether there exists an aperiodic monotile, meaning that copies of this tile can only be arranged in a non-periodic manner in the Euclidean plane. And this was a long-standing mathematical problem, and it was solved last year by David Smith et al. In this reference. And they gave a family of blocks, a family of tiles that tile the plane only aperiodically. So if you take this tile, there's only one way to assemble it in the plane such that there's no gap between tiles and the whole plane is tiled. So, and we use this tile to construct an interlocking block, which you can see over here. And of course, we gave a construction, and now we want to see, okay, is our construction yielding a topological interlocking assembly? And this is how where our package comes into work. So by proving it, what is our workflow? First, as you can see over here, we start with 3D printed models, and try to get a feeling of, okay, is our assumption true? Could it be a topological interlocking assembly? And how can we choose the frame in order to establish this property? Then we translate this problem into a linear program and give this problem to the jump, and jump is going to solve this problem for us. So it's going to give us the solution to the linear program we derived in the second step. And we have set it up in such a way that if the solution is trivial, then we have indeed a topological interlocking assembly, and if there is a non-zero solution, then we have no information. So over here you can see an output, a part of our implementation, or like of our Julia call. So we have implemented this function TI test, which is just topological interlocking test, so abbreviation for that, and it has its input assembly, which is an assembly of blocks, and a frame, which is a subset of the assembly. And by calling this function, we are going to do this processing and deriving this linear program. And at the end, you can see this information for us that yes, the assembly is topologically interlocked. Okay, and one might think that our journey ends here. So after constructing, proving, and getting this output, that our work is done. But that this is not the case, because we are part of the Collaborative Research Center CRC-TRR 280, where we are in contact with civil engineers to actually come up with new approaches to construct structures with carbon concrete. So this is part of our research team in Aachen. And you can see we are standing on a structure, which is indeed this structure over here. So as part of this research center, we 3D printed these blocks out of carbon concrete and built it in real world, and you can see that it's actually stable.
All right, let's go over some other features we've already implemented into our package. How does our workflow go? Well, we are mathematical researchers, so we basically implement the features in the order we need them. If anything new comes up, we implement a new feature and go on like this. We have a random simplicial surface generator, which is very important in order to validate our code, to construct some examples and not having to do everything by hand. We have also the possibility to merge different polyhedra along matching faces. So let's say, for example, we have two cubes which are congruent, so have exactly the same faces, and we want to just glue them together at one face. We can do this using our program, and we've also constructed some topological interlocking blocks out of smaller, simpler blocks by abusing this method. Of course, orientation, I've already talked about it. We need to orient our surfaces or our polygonal complexes in order to define this half-edge data structure. But on the other hand, it is used in order to calculate, for example, outward normal vectors. And we also have methods for triangulation of the face of our polygons or polyhedra, which we obviously use in order to plot our surfaces. We need to generate the mesh for this. Okay, we also have a struct for edge color surfaces already implemented. Once again, what are those edge-colored surfaces? They translate for us geometrical objects with congruent faces, which are of particular research interest to us. So we already have a way to express those in our code. Other open questions include to actually calculate maybe all those colorings of the edges, but this turns out to be a very complex problem. And we also have the possibility to flip edges in our simplicial surfaces. So take an edge which is adjacent to two faces. We flip it by removing those two faces and adding two new ones where the edge is actually perpendicular. And last but not least, if you remember this moving picture, the GIF of the Bricard octahedron, this was a flexible polyhedron. And the opposite of flexible is called rigid. and there is a criterion for rigidity of such a simplicial surface or of such a polyhedron, which is based on linear algebra and the so-called rigidity matrix. We've also implemented a way to calculate this rigidity matrix, and then a simple rank computation tells us if a simplicial surface or if a polyhedron is rigid or not. What do we still want to do? As I said, this is our research code. So as of now, I think not many people may use it or are able to use it because of lacking documentation. So this is one very, very big point on our to-do list, to actually give a good documentation motivated by examples and make this available to everyone. But then when we come to like subject matters, there's another rigidity test which is not as restrictive, but actually computationally more expensive, as it needs to use semi-definite programming. This is where, thankfully, JUMP comes to the rescue. We want to exploit the JUMP and its solver ecosystem in order to implement this rigidity test. We also want to give algebraic conditions, which are polynomials, in the vertex positions of our simplicial surfaces for the existence of flexes. So this would be a polynomial. You plug in the coordinates you want to have for your vertices, and if the result is 0, then you know, okay, my surface will have a flex. And this needs the so-called bracket algebra, so an algebraic mathematical object. So obviously we need some capabilities for symbolic computations and Gröbner bases because of the multivariate polynomials that show up. And thankfully Julia also has already some packages which do this for us. We have abstract algebra for handling multivariate polynomials, Gröbner.jl for Gröbner basis computations, and I want to emphasize also the OSCAR project, which is a computer algebra system which is developed on top of Julia, combining the capabilities of multiple computer algebra systems, and is also a German Research Foundation funded project and co-developed by people along our floors in our office, so that's also great. Yeah, the embedding problem, where we have given edge length and a combinatorial structure and want to get out the vertex positions up to isometry. We want to once tackle this numerically. The equations that show up are polynomial equations of degree 2, so one way would be to naively just try to solve it using, for example, nonlinear solve.jl, but there are also nonlinear optimization approaches and methods of numerical algebraic geometry, which are, for example, implemented in the package homotopic continuation.jl. And last but not least, we also want to tackle this problem algebraically, so give exact positions of the vertices under edge length constraints. And once again, we need Gröbner basis capabilities, but also methods out of real algebraic geometry. Okay, so what I want you to take away from this slide is not the details of everything, but more so the right side, that you see, okay, we really are able to exploit the Julia ecosystem, and we are very thankful for the work many people put in, and for this great programming language and the community around it, that we are able to just take somebody else's code, adjust it to our problem, and put this all together in one package. So thanks a lot for listening to us, and now we are happy to answer some questions.
Thank you for your fantastic presentation. Next, I'm not sure about the name. George Dasseris, our next presenter. Thank you.
Right. Oh, cool. Right. Great. Welcome, everyone. So this talk is directly linked with a previous talk on floor 3. Unfortunately, we are in different rooms. What I will present is related with continuation in dynamical systems, but I'm very excited because I will present some recent and different methods. I'll make sure to introduce the topic as, let's say, as easily as possible. So I'm interested in multi-stable dynamical systems. What does this mean? This means that there are at least 2 attractors for this dynamical system. An attractor is a generalization of the concept of a steady state, because it can be either chaotic or periodic, or to be actually steady, like a steady state. To give you some intuition, if you have heard about ecosystem dynamics, one possible state of the system would be a coexistence of various species in the population, but an alternative state would be some species die out, or all species die out. These are possible states of a system. If you think about climate, perhaps you have heard about the glacial and interglacial states of the planet, or you have heard about ocean circulation being on or off. Now, my favorite example is very simple. It is called a magnetic pendulum, and you see you have an electrically charged pendulum hovering above 3 magnets. And if, let's say, I start the pendulum at this xy coordinate and I let it go, I know guaranteed from the dynamics of the system and the physics that it will stabilize over one of the three magnets. Now, what I'm interested to know, therefore, is given I start at some xy position, which magnet will I end up to? And this is called the basins of attraction. And this beautiful picture over here is exactly this plot. So if I start at this xy coordinate, I color this point purple because I will converge to the purple magnet. And I want to obtain this information for multi-stable dynamical systems. So what is practically relevant for such systems? First of all, find all the attractors they have, and then estimate their basins of attraction. And if it's not computationally feasible to do the entire thing, get some sort of proxy for these basins of attraction. Now, what is interesting is that multistability can be quite complex, and you can have some beautiful examples where there are some chaotic attractors, and there are some periodic attractors, and all this business can get very complex very quickly. So not only you want to find all attractors, but you want to be sure that you can accommodate chaotic attractors in your search. So how would you do this in practice? There are various methods. The ones that I use the most are the following 2. One is called featurizing and grouping, and it is conceptually the simplest method in my opinion. So let's say that you have a system that has 3 dimensions or 3 variables, and what you will do is you will simply populate the state space with random initial conditions, and you will evolve all of these initial conditions. So every initial condition is a trajectory in the state space. Now, every trajectory you collapse into features. That means for every trajectory, I calculate some descriptive numbers for it. In this particular example, I just get the minimum of the x dimension and the standard deviation of the x dimension. And my hope is that different attractors of my system will have sufficiently different features. So then I simply group all of these features. I cluster them using a clustering algorithm. And the hope is that each cluster will represent a different attractor of the dynamical system. Now, this is fine and all, and works very well with literally anything. I have applied this to spatiotemporal climate models, and it works well there. But the downside is that you don't know really in advance which features will be good at separating the different attractors, because some features might mix the two different attractors, but mix them as one. Now, an alternative method that I'm particularly proud of is called the recurrences method. And you see that in the theory of dynamical systems, there's this property that if you converge to an attractor, so here you see we have converged to this periodic kind of behavior. Let me pause the video. That's not so easy, but okay. Anyways, you see that as you go around, you return to a point you have been before. And we abuse this fact, so to speak, to find out where attractors will be in the state space, because this is when you will have this so-called recurrence. Now, this is very nice because it is based in very solid math, but perhaps most importantly, this method is extremely robust and it is very easy to resolve a failure. So if this method fails, you know exactly why and exactly how to fix it. It also has very, let's say, very small requirements. It only requires as input a state space tessellation. So make a grid of the state space, and that's all you need. Now, when we published this work, it became the feature article, which means that let's say the editors felt that it was one of the journal's best publications, which of course I'm very happy about, and I think it deserves it as well. So you have a method that finds the attractors of a dynamical system. Now, what do you do when you have the attractors? Well, the most basic thing you want to do is to quantify their stability. You see a dynamical system or a model will have some parameters, and you want to see if I vary the parameters of the model, how will the model behave? Will this attractor remain stable or not? So in the magnetic pendulum example that we have here, you see that the pendulum, I colored it green because for this configuration, it will go into the green magnet. Now what I'm doing is I'm decreasing the magnetic strength of the green magnet, and maybe you can see it, there is this dust line around the magnet that represents the basins of attraction. And here the pendulum is gray because I'm not sure whether it will converge to the green magnet or the purple magnet. And if I decrease the magnetic strength even more, then I'm pretty sure now that in fact the pendulum will not go to the green magnet at all. So this green magnet has lost stability. Of course, you can say similar examples, for example, in predator-prey models, so ecosystem dynamics. If I have a predator that is bunnies and I have a prey that is carrots, I may have two attractors in this model. One is coexistence of bunnies and carrots, and one is a state where all the bunnies are dead and only carrots exist. And if I start here, I'm very confident that all of my possible initial conditions will go to the coexistence attractor. But let's say I'm increasing the consumption rate of carrots as an exemplary parameter, and now I'm not so sure anymore if my states will go to the coexistence because the coexistence has lost stability. You see, its basin of attraction has been decreased into this dust curve. And if I continue to decrease, I lost all confidence that I will go to the coexistence and all the bunnies will die, and I don't want to do that. So that's why I want to do this analysis. Right. Now, how do you do this analysis so far, and how I think you would do it realistically if you have a real-world system? Now, so far, for the last 4 decades or so, this type of analysis is done with what I call traditional local continuation, which is the type of software like auto, matcont, and bifurcation kit that was the talk before. And the way this works is that you track the linear stability of a fixed point or a limit cycle as you vary a parameter of the system. This doesn't do multi-stability automatically. You have to manually find all attractors in the system. But this is how it looks like. If you do this numerical analysis, you have such a typical plot where the x-axis is the parameter and the y-axis is some numeric value of the attractor. Here is the maximum of the x dimension, let's say. And the plot has binary information. If the line is solid, this state is stable, and if the line is dust, this state is unstable. And you see here you have a stable state, and here you have a stable state that is actually periodic. So this is great. But you see, linear stability means response to infinitesimal perturbation. And unfortunately, in the real world, there is no such thing as infinitesimal perturbation. All perturbations are finite. Now, recently, it has been made quite apparent that this linear stability framework does not really, or is quite limited when it comes to real-world applications, exactly due to this fact. So I will show now a concrete example of how this can happen. These are the basins of attraction of the magnetic pendulum, if you remember, and what I'm doing here is I'm decreasing the magnetic strength of the purple magnet. So this is a snapshot where the magnetic strength of the purple magnet is decreased, which is exactly why this purple region is smaller than the blue or the white region. So what you see on the left plot over here is with the cyan curve is the linear stability of the purple magnet, which is the quantity you get with the traditional local continuation. And you see, even though I decrease the magnetic strength of the purple magnet, this number is completely constant and negative, which means linearly stable. And only when when the magnetic strength becomes exactly 0, this number jumps and becomes positive, which means this is linearly unstable. What I'm showing you with purple is simply the fraction of the basins of attraction of the purple magnet. This is simply how many initial conditions go to this attractor. What is the proportion from all of my plausible initial conditions that will go to this magnet? Naturally, the smaller this magnet, the smaller this number, the weaker the magnet. So this makes sense. And you see here that the moment I start decreasing the magnetic strength of the magnet, this number that is called capital F, and it is the purple curve here, this number decreases continuously to 0. Not only that, but perhaps even more importantly, this number becomes practically 0 already at parameter value 0.2. So this means that the linear stability is, let's say, misleading at this region because it says that, oh, this attractor is still stable at these parameter values, but in reality there is almost no single initial condition that would go to this attractor. So that's what I mean, that in the real world, the linear stability can be very limiting. And that's why a non-local view of stability is typically a better indicator of stability for finite-sized perturbations. And there are many ways to quantify non-local stability. The default one I used was this fraction of basins of attraction. Right, so now the question for us was, how can we make such a similar framework that instead of having the local stability or the linear stability, it gives you a global stability. And this is where we devised this algorithm for global continuation that once we published, it also became a featured article. So I'm very happy about this work, as you can imagine. Right, so how does this algorithm work? I think conceptually it is simple. You will be the judges of that, of course. Now remember, we already have algorithms and infrastructure to find attractors and basins of attraction at some parameter. And this is our starting point, actually. So we start knowing the system attractors and their basins at some parameter P1. We then do what we call a seeding step, where we seed or we select some special initial conditions that are sampled from the attractors we have already found. And then we simply map or attribute these initial conditions to the new attractors now at the new parameter value. So after we seed the initial conditions, we change or we increment the parameter we are interested in, and then we find again the attractors. After this step, we perform a full basins estimation where we try to find as many attractors as possible, if more exist in the dynamical system for this parameter, and also estimate their basins of attraction. And this method may find, of course, more attractors. And the last step is the matching step, which, to my knowledge at least, is something completely novel. No other continuation software can do this. Which means, what does matching mean? Well, if we label attractors by color, so each attractor is labeled by the positive integers or whatever color you want, and the color an attractor gets is random because there is no preference over colors. So what we want to do is establish a continuity. That means if the purple attractor at parameter P1 is very similar with the red attractor at parameter P2, this should get the same color, and this gives you this continuity of attractors as you change parameters. And this matching is actually completely configurable by the user. And what happens in this particular example is this purple attractor and this red attractor are both periodic, and they are at approximately the same location, so they are matched. They get the same color. While this green attractor is just a fixed point in the state space, while here it is a limit cycle. And I want them to be different, so that's why this yellow attractor remains yellow and does not become green. Right. So what is the output in the end of the day of this continuation? On one hand, you have the fractions of the basins of attraction for each attractor. So in this starting parameter, you had, let's say, 40% go to green attractor and 60% go to purple, and et cetera, for all parameters that you are interested in. And of course, you also get the attractors themselves at each parameter value. And you get all attractors automatically. You don't have to restart this process or do it several times. You simply start it, let it go, and it does everything for you. And it finds new attractors if they pop up at a new parameter, and it can also find chaotic attractors. So this is supposed to be a chaotic one. I don't know if you can see it or not. I hope you can, though. Right. So for me, this is kind of a new era of continuation, because while the question at hand is the same, what is the stability of my system versus a parameter, the way we actually do it is really fundamentally different. So what I'm trying to do here is on the left compare the traditional way that you would do this, that I did using bifurcationkit.jl in Julia, and also let's say the new way that we do it. The reason there are two plots on the left is because you have to do this process as two steps, and you manually have to do the second step. So you don't get both attractors automatically on the left process. Right, so what is the comparison? Just to be clear, I'm presenting my work. I'm very biased, and I think my work has much more positives than negatives. Of course, you can see the full comparison that we have in our paper for a much more holistic view, right? Right, so this traditional method only finds fixed points and periodic orbits, limit cycles. However, sometimes it may struggle to find limit cycles, while our method finds all type of attractors, including chaotic and quasi-periodic, and so far everything we have tested it for. On the left, you have the linearized stability measure or quantifier, while on the right-hand side, you have a non-local stability measure that is superior in the sense that if something is non-locally stable, it is guaranteed to be locally stable. But the other way around doesn't work. If it's locally stable, it doesn't mean it's non-locally stable. Yeah, automatic multi-stability as well. And of course, in the left side method, you get unstable states, so branches of unstable fixed points or unstable periodic orbits that you don't get from us because we only find attractors. Although I have to admit, personally, I'm not particularly worried that I don't have the unstable states because I use dynamical systems for the real world, and in the real world, there is no such thing as an unstable state. An unstable state is one that even an infinitesimal perturbation will make you go away from such a state. In the real world, there is no isolated system. Every system is subject to infinitesimal perturbations because the wind blows or whatever, so you cannot observe unstable states in the real world, as far as I know, at least. Right. And performance comparison, full disclosure, bifurcationkit.jl is optimized for PD problems, so very, very high dimensional dynamical systems. Our code is not. And the system I compare here is only 3-dimensional, so very heavily biased in performance in our favor. But to do the linear stability analysis, you need 10 seconds, and to do the global stability analysis, you need 20 seconds. So from this perspective, BFKit is twice as fast. However, this code on the left has only used 2 initial conditions, while our code has used 1,000 initial conditions, so that it can find all attractors that exist and can also quantify the non-local stability. So if you normalize per initial condition, we are 500 times faster, approximately. Great. So how do we put this all together so people can use this easily? We developed a framework, which is the package attractors.jl on how you can do this. And the central structure, let's say, or the central struct of this package is what we call attractor mapper. And this is simply instructions for how to find attractors of dynamical systems and nothing more at an abstract level. And of course, it has various inputs. But the key part here is that you simply use this key structure with a function called basins fractions or basins of attraction, and this will find all attractors for you and compute their basins of attraction. Now, what I'm very happy about is the way we designed our output. Our output is just standard Julia dictionaries that map attractor ID or attractor label to the attractor set, the set in the state space. So this is important because it is extremely simple to understand such an object. It is just a standard Julia dictionary that almost everyone already knows how it works. It is not an extremely complicated output with hundreds of internal fields and hundreds of internal references, so you can just use it. You don't need automatic methods that do analysis of this object for you. And of course, because the library is hooked up with dynamicalsystems.jl, you can analyze all these attractors further in terms of other measures of non-local stability or whatever other measure you want to do. Right. Now, when it comes to the continuation, the way we do global continuation, in fact, we simply reuse this existing infrastructure. So the input of our second central, let's say, structure of the attractors.jl package. So we just take the attractor mapper and put it into a global continuation algorithm. And of course, we may put other options as well in there. But then we simply give this continuation algorithm to the function called global continuation that I hope the text is large enough. Yeah, it looks large enough to me. Right. So you put this in there, and it gives you as output this global continuation that I presented in the slide before. And once again, this is a very simple struct. The output is a very simple structure. It is just vectors of dictionaries. So for each parameter value, you have the dictionary that you would have obtained in the single parameter analysis case. Now, something that I'm very happy with and that we put really a lot of work in is to make this infrastructure completely extendable. And by extendable, I don't mean in the sense of open source code. You can always extend open source code because you can just copy it and write whatever you want. That's fine. By extendable, I mean that there is a clear developer documentation on how you can extend this. For example, if you want to create a new mapper, a new way to map initial conditions to attractors, you simply have to define a new type, of course, and then simply extend a single Julia function that does this, and then your new mapper will integrate with everything else that is on this picture. You can do fancy non-local stability analysis, you can do global continuation. And in fact, you don't even have to be part of dynamical systems.jl. If, for example, you don't like our logo and you think your code should not be there, that's fine, actually. You don't have to. Just make sure that you extend the same function, and then I can use your code and you can use our code, and then everyone is happy. Right. Just a side note, this kind of global stability scientific research was inspired initially by truly really complex systems, by dynamical systems that approximate real-world power grids, particularly one paper here, particularly the power grid of entire Britain, brain networks. So these are really complex systems, and to really drive the point home, I have an example here from one of my colleagues and another developer of the attractors.jl library, where he uses a network of 100 coupled Kuramoto oscillators. So this is like you have a dynamical system that is simple in itself, but you couple it with 100 copies of itself. And this can generate extremely complicated dynamics, but actually we have applied our methods to this system, and this is the output you get, and everything appears to just work fine. And this dynamical system has hundreds of coexisting attractors. Some of them are fixed points, some of them are limit cycles, and you see the method finds all of them and continues all of them automatically to the point that there are so many that visualization has become completely useless even. The method yet still works. Right. So how would it look like if you wanted to run some code that does this kind of things? Well, I have a code snippet over here. I hope it is large enough. Seems okay, right? So the way it works is that you have a simple 3-step process. The first step, the first code snippet, is that you define a dynamical system. This is very general throughout the library, and in fact, the syntax is also identical with SciML, so everything is integrated well together. Once you have a dynamical system, here this is called the Henon map, for example, then you have to create an attractor mapper. Here I use this method by recurrences that I presented in the start of my presentation. And the only thing this recurrences method requires is a tessellation of the state space that I create here with the x and y variables. Of course, there are some meta parameters as well that you may tune if you want to. And then you simply give this mapper to one of the library functions. Here I call the function basins of attraction. The output is a standard Julia array. But also for convenience, there is a convenience plotting function that can plot this array for me. And if I plot it, this is what I get. These are the basins of attraction and the attractors. You see one attractor, this triangle, is a period 1 orbit, so a fixed point. And one attractor, the green one, the green rectangles, is a period 3 orbit. And the the purple region is the basin of attraction of the fixed point, and the green region is the basin of attraction of period 3. Now, something that is, to my knowledge, unique feature of our software is that it also gives you the exit basins. You see, this plot has 3 colors because the gray color is trajectories that have diverged to infinity. In fact, for our software, infinity can be just considered another attractor, even though mathematically this is not very formal. Right. If you want to do a continuation, so take all of these attractors and see how their stability changes as you change a parameter of the system. It's also very simple. There are 5 lines of code here of how you do this. You create a global continuation algorithm from the mapper. You see here I simply reuse the mapper. And I also have to create a state space sampler, which means how I sample the state space. Here I just do it uniformly because I have no reason to do it differently. And then I simply call the global continuation function that will give me a vector of all the attractors at each parameter and a vector of the basin fractions at each parameter. So this is a very simple data structure, but there is also a convenience function to plot it if you don't want to do anything, to write your own code for plotting. And this is what you see, which is the top panel is the basin percentages. So what percentage goes to the purple attractor, which is the fixed point. What percentage goes to the green attractor, etc., etc. And you see there are more attractors found here that I haven't shown in this plot. Right. Now, what's coming up next? This is something I'm very excited about because you see so far, for the last literally 4 decades, all this continuation infrastructure has been in completely separate software that have never communicated with each other. Like if you have a dynamical system, you want to do a continuation. You also want to compute the Lyapunov exponents. well, tough luck. You have to write your code twice because there is no way for your code to access these two types of libraries. So what I'm hoping for the future is that we have local and global continuation together, so that someone that is interested in local continuation can also use our tools for global continuation. And we can use the output of our global continuation and do local continuation. And thankfully and happily, I also talked with the developer of bifurcationkit.cl, and we seem to agree on this picture. So I think in the future, we really have a bright future for dynamical systems in Julia, because our methods don't exist in any other programming language, and coupling them with traditional continuation will yet again be a total novelty in the world of dynamical systems. And of course, the basis of all of this, at least what inspired me, is a new Google of Summer code project that is called periodicorbits.jl, whose purpose is just to find periodic orbits of a dynamical system. No continuation, nothing else, just give me the periodic orbits, and that's where it stops. Now, the dynamical systems library, we have put a lot of effort to make the source code as clear and as accessible as possible. In fact, that was the #1 priority for 7 years ago that the library started. And I think we really are doing a good job. So if you're interested in these things, please do consider to come along and make an overarching software for the whole field of nonlinear dynamics, so we can finally end this situation that there are 500 software, each with 1 or 2 functions, and there is no way you can use all of them together. Right, so that's it for me. Thank you very much for your attention, and thanks also to Khalil and Alex, who are the 2 other, I would say, main or lead developers of attractors.jl. Yeah, and if you have any questions, let me know. Thanks.
Question?
Yeah, thanks a lot. Very interesting. I was wondering about a slightly higher dimensional setting you showed when you did for these 1,000 initial conditions, that you would put all these initial conditions in your state space. How does this work, for example, in the case where you had 100 dimensions? Does it then still cover the space?
I mean, that depends also a bit on your space, right? For the Kuramoto networks, that's, at least in this example, clearly not a problem. But of course, the Kuramoto networks have a bounded state space. So they are phases. So all of them go from -pi to pi. So there, perhaps you can cover it well. It really depends a lot on your physical system, right? And how dense of a covering you want for a particular dimension. The good thing here is that you are the one that tells us how to do the sampling. So you might say, oh, for this variable, let's say it's temperatures, you have a climate model, sample extremely densely in temperature, but for humidity variable, I don't care, don't sample as densely. So it's up to your physical problem.
Okay, thank you.
Next question. Well, first of all, thank you very much. It was really interesting and also an amazing package, the whole dynamical system.
Thanks.
And what about if you have many parameters? And because, for example, here in the Kuramoto, you have to select just a few or 1 or 2 parameters to do all the analysis. Can you do it with multiple parameters at the same time?
Yes, but in nested for loops. Notice that the cool thing about our approach is that the actual continuation step is in fact entirely orthogonal to the finding attractor step. So what I do when I want to explore many parameters at once is I simply get the attractors at each parameter individually, and then I call my matching routine. So across the parameter space, the attractors get the same color. So that what I mean by that is that I may have 3 parameters, and I will say, okay, I create an arbitrary curve I want in the parameter space. Let's say some curve that is in a parameter space. At every combination of parameters, I get the attractors. I can do this individually. And then what I do is I simply call my matching routine on all of my individual attractors that I got. And what this will do is it will make, okay, if I have a limit cycle that exists throughout this spatial continuation across any curve in the parameter space, it will have the same color at every point. So I don't know if this answers this question that you asked. This is how I approach multi-parameter simulations. We don't have codimension 2 continuation, which is something different. because this is tracking a bifurcation, not the attractors themselves, and we don't calculate bifurcations at all in this software. So continuation across multiple parameters, yes, very easy. Tracking of codimension 2 bifurcations, not possible at all. So it just depends on what you're looking for.
Okay, well, thank you very much.
Next question. Maybe one question. So you said that there's already like this kind of there's all these packages in different environments and whatever, and now one can say, okay, now you even make a new package in a new language. So as another scientist, you now have to install this new Julia language and figure out what that's about. How did you find the kind of acceptance in the scientific community, or I guess you got your paper published and featured, so the publishers were apparently happy with it. But what was your experience with kind of pitching Julia like that?
Very poor, actually. Extremely poor. Unbelievably poor. It's really shocking to me how someone that is just 10 years older than me has an absolutely, completely different mentality. And they truly believe that it is better for everyone to write their Paleolithic script that no one can reproduce and then just put it, not even put it on the internet. And that's what people think is the okay thing. This is what gave birth to dynamicalsystems.cl, by the way, when I was tutoring nonlinear dynamics, and I was like, yeah, my students should compute the Lyapunov exponents. How hard could it be? 5 million people have done it already. Well, it turns out they have to do it from scratch on their own. I'm like, okay, that's ridiculous. So I'm really waiting for the new generation of professors to come along where they have really appreciate open science and all of us communicating on the same code or on the same interfaces. It doesn't have to be the same code as I pointed out, but it can be the same interfaces. So I'm really looking forward to the future of a new generation that appreciates open science and open code more, and perhaps there the reception will be better.
And do you think it's worth it to like write kind of an R interface or some Python interface, or would you say that doesn't really solve the problem?
Oh, you could use this with Python code. Okay. That's as far as I know, this works no problem. But come back to me if this doesn't work. As far as I know, you can just do this. But yeah,
thanks.
You are welcome.
Maybe the last one.
Thank you. It was a very interesting talk. I'm just interested in how long are these trajectories that you need in order to say that you have reached some form of convergence? Because if I understand correctly, you sort of run these along until you have some sense of
Yes.
coherence.
Yes.
Does this...
Right. So it depends on the algorithm. The algorithm on the left is not auto-terminating, so you, the user, decides how long they have to run, and you have to be confident that this is long enough. The algorithm on the right is auto-terminating, and what you, the user, decides is how many recurrences should occur before there is an attractor. So you can set this confidence, but at least to my knowledge, there is no way to predict how much actual time 500 recurrences means. Because especially in chaotic systems, I'm sure you cannot predict that, but maybe you can prove me wrong, but I haven't found a way to do this deterministically. So it's that's why I have here the either good or bad. It's good because I'm confident that it worked if it stopped, but I'm not confident when it will stop. Yeah. In general, it's fast though.
Okay. Thank you. Thank you.
You're welcome.
Okay, hello everyone. Welcome to my talk about QML.jl. So just to be clear about any ambiguities, this is about graphical user interface toolkit based on Qt. Also welcome to everyone online. I hope my son was also able to join me online, but we'll see tonight if he watched the stream or not. So QML.jl, this talk is mostly about what's new, but still before starting, we'll take a look at what is the traditional buildup of a QML.jl program. So it's based on the Qt graphical user interface toolkit, which has itself two components. One of these is QML, which uses a separate markup language for the graphical user interface. So basically you need a Julia program and this markup file. The data exchange then happens through different kinds of connectors that we will illustrate using this simple toy problem here. So basically you write a Julia code where you have some observables, standard Julia observables that you connect to the graphical user interface. You can also make functions available on the QML side using the add_QML function macro, and then basically you just load the QML file, introduce the observable as properties, and in that sense you can make the GUI that we saw previously work. The QML file is basically a list up of different components, the main one here being the text field that when you enter a value will double this value by calling a Julia function. So that's a very simple example. So now I want to highlight what is new and the kind of program that we will make during this presentation. So the main novelty of the QML.jl with respect to the last major release is that we upgraded to Qt6, which gives all kinds of enhancements. But also we introduced a table model, so the example application here will be used to do all kinds of manipulations on a Julia data frame using the graphical user interface. So it will allow us to insert columns, delete columns, edit the values of data like we're doing here on the standard iris dataset that comes with data frames. And when we finish manipulating the dataset, we can then save the file. Here I had already a file that had the same name, but because it's a big standard GUI toolkit, you see that it automatically thinks of asking you if you want to destroy your own file, so I didn't have to do anything for that. And then we can load back the file or load another file. See that indeed it can load the second file without crashing, and then load our original file again to check that indeed the saved file is what we get back with the renamed columns and the incorrect values. And also on the Julia file you have immediately the data frame as it was manipulated in the GUI, so you don't necessarily need to save it. So to make this application, the first step here that I wanted to show is that you can make it in a kind of graphical user interface design tool, since QML is used by quite a lot of people. There are some tools that exist to manipulate it, and I forgot to start the movie here. So the Design Studio, basically, I will skip over it quite quickly. It allows you to, using a drag and drop interface that I must admit is a bit frustrating for me at least, but I'm not a GUI design expert, allows you to draw up the GUI. So here we use this tool to make the global layout of the application, replacing the table view with a white rectangle, because unfortunately this tool does not support the table view, even though table view is a QML component. Not all QML components are supported in this tool by Qt themselves. So once we have the QML, to load it into Julia, you need to make a few small changes, but these are fairly minor. As you can see, this is the complete diff that you take from the automatic QML to the Julia file, or the Julia compatible QML file, let's say, and then we can load this into our Julia code. So here The bottom of the file is the same as before. We have the call to load QML to load the file. Before that, of course, there's a few more things because we now have a fully functional data frame editor. So what are the main things that we need to do? We need to override a few functions to allow setting and getting of the headers, setting of the elements. And then we have the longest function is actually the one to load the data frame, because there we'll do all the setup to set the headers and to set actually the Julia table model. So the table model itself, it is then communicated using here this Julia properties struct, which contains all accessible properties, which is defined at the top here. So here we have the actual table model, which by default will be empty until the user clicks the load button. So the Julia code itself is quite simple and consists of only standard Julia functions using basically a kind of translation between what the QML table model interface expects and what is exposed by the data frames. And then we can use this in the QML file itself. And so you see the key component here, which I will just show, is that you have a standard table view component, which as a key property has the model itself, which will be more or less directly our data frame, slightly translated sometimes using the functions that we provided. So I'll not go into detail in the interest of time. One new feature I wanted to show, which was thanks to Jannis in the room here who requested it. You can now modify a single, if you work with one main QML file, you can just modify this, and if you save it, automatically you will see the update in the running Julia program on the GUI. It was, for this functionality, not hard to do, but it needs a bit more extension. So yeah, what is new, I already briefly mentioned, the model and the fact that we are in Qt 6 now. One important consequence of that is that we can use Wayland. The live coding I've shown also, and the new version also comes with a bit more robustness. What I hope to do in the future is to improve support for Maki, so for the plotting toolkit. Maybe split off this data frame support into a separate, more elaborate package so that you can just have data frames widget in any GUI that you want to make without having to repeat this code. Live coding needs to be extended to multiple files. I also want a web view, but this requires compiling the Qt web view component, which contains Chromium. Compiling that on Yggdrasil with binary builder is not so easy. And threading integration is also still a work in progress, even though the base functionality in Julia to allow foreign threads is there. So that concludes the presentation. If you have any questions.
Can you comment more on this threading integration, what you mean with that?
Which threading integration? So it's possible to have foreign threads in Julia so that you have a thread, for example, the rendering thread in an OpenGL Qt application. If you do nothing special and it calls a Julia function, the application will crash. So Julia now has functionality to register these foreign threads, but I tried exploiting this and there were still problems, like it didn't crash anymore, but I got a kind of lockup and I haven't had the time yet to investigate why it doesn't work as it should at the moment.
Thank you. Next question. Okay. No question. Thank you.
Thank you.
start? All right. So, yeah, thank you for coming here to my talk. Today, I want to talk about automated theorem proving with DL in Julia. So, let's get started. So, I'm hoping to answer 3 questions with this talk. So, what is automated theorem proving? Why is automated theorem proving important? And what technologies enable automated theorem proving? So first of all, a little bit about my background. So I'm a researcher at KIT in Karlsruhe, and I'm researching methods for verification of cyber physical systems. So systems like cars, planes, or robots. And I'm currently working on a project to integrate theorem proving with Julia. So let's start with an example. So let's say you have this model in modeling toolkit. So you have some variables, and this model models a heating system. So let's say this variable x is a temperature, y is some internal variable, and u is a control input of this system. And you have some dynamics. So somehow the dynamics of x depend on x itself and y, and y is somehow influenced by this control input. And then you have some event here on the bottom, and this gets triggered each time the temperature hits 19 degrees Celsius, and then you are turning the heating system on. So this is like a very simplified model for this heating system, but maybe let's look at this further. So what does this system look like? So maybe let's look at a plot. So initially, we start at some temperature, and the heating system is turned off. So the temperature is decreasing, and at some point, our event gets triggered, the heater gets turned on, and then it will just continue to heat the system. Of course, in a real-world setting, you would also want to turn it off at some point because it's getting hot in here. But this is just one possible trajectory of the system. So what if you had some uncertainty in your system? So what if your initial condition is not like a point, but it's some set? So let's look at this. So these are now like several trajectories of the system, and what we can see is, the behavior is like quite different in these scenarios. You always have like this kind of dip, but sometimes it's going up first, and so so there's some variation in this behavior. And now someone, like for example, you're working with a company, and they tell you, okay, it's bad if the temperature goes below 17 degrees Celsius. So this should never happen. Maybe like our product will get destroyed. So how do we make sure that this is always the case? So maybe let's look at this differently. So let's look at this in phase space. So we have our 2 variables, x and y. And this blue box right here is our initial condition. So our initial condition is somewhere inside this box. And now let's simulate again. And this is what the behavior of the system looks like. So you can see there's like this edge in the graph. So this is where the event gets triggered, where you have like a discontinuity. And like judging by this plot right here, the temperature is never going below 17 degrees Celsius. So we're good, right? I mean, that looks pretty convincing, right? So the thing is, how do we make sure that we haven't missed something? So we have simulated some trajectories, but we haven't simulated all trajectories. So what can we do about this? So one way would be, okay, let's just simulate even more trajectories. Like maybe we can try to cover all the initial conditions like very tightly, and then we are done. But yeah, but maybe we need to simulate even more. So what can we do? So one approach would be to solve the equation analytically. So this is what the equation is in mathematical notation. So on top we have our differential equation, and it's a linear differential equation. Then in the middle we have our control, which is pretty simplistic, and on the bottom we have the condition we want to prove. And so we might approach this by actually solving this equation, then plugging this in and solving for the time of the event. And so maybe we could solve this analytically. But to me, this feels very cumbersome and error prone. I don't trust myself to do this correctly. I mean, you might have some experience with solving these equations by hand yourself, and like at least for me, most of the time I make some errors and then the results don't match. So this is, yeah, might be a dangerous thing if you really want to trust your solution. And also that this feels like a step backwards. So we have all these fancy tools in Julia to look at our differential equations, and now we're going back to paper and doing it all manually. So I don't know. And also, if we have more complicated systems, we might not be able to solve them analytically anyway. So this is, yeah, for this system this might work, but in general, how do we deal with this problem? Yeah, but what if we could automate this? So this is where my work comes in. So on the left-hand side, we have our MTK model, but now you might notice that we're using a different macro in the top left. This is my tool I'm developing right now, which I call AlignShots. And on the right-hand side, we define our model, and then we have this check macro. And on the top, now the colored condition is the thing we want to prove. Then in the middle, we have our assumptions. So this was the initial condition I showed you earlier, the box. And then we have this mysterious invariant. And if you run this, the code will tell you, yes, it was proved automatically. So how does this work? I mean, it might say it proved automatically, but if you don't trust this, then yeah, it's worth nothing. So let's see what's behind this technology. So as you can see from this graph right here, you have your MTK model, and you can use my tool to convert this to a DL model. So DL stands for differential dynamic logic, and this is a formal language to express these systems. And then this formal representation gets sent to a theorem prover. Also by my tool, this was this check macro. And then the theorem prover checks my model and sends back a response which then appears on the Julia side. And this is like the high-level overview. So let's go into more detail. So once again, on the left-hand side, we have the MTK model, and now on the right-hand side, we have a hybrid program. So this is the modeling language inside of this differential dynamic logic that is used to express these kind of systems. So let's go through this expression to see what's going on here. So on top, we have our assumptions. Then here, this is the event that takes place. And it might be like a little bit unfamiliar for you, but this question mark, this is a test. And basically, if this test gets passed, the execution gets continued, and otherwise it gets stopped. And then this plus symbol right here is a non-deterministic choice. It's a little bit similar to an if or else, but it chooses either the left-hand side or the right-hand side, but there's no condition on it. So it's a non-deterministic choice. Then here on the bottom, you have the differential equation. And then there's also something that might not be familiar. So there's this so-called domain constraint after the and symbol. So this takes care of this event being actually triggered. And then here you have this these rectangular brackets, and this is the so-called box modality. And here we are saying that after every run of this hybrid program, we want to ensure that this condition that the temperature is greater or equal than 17 is true. So this formally describes the thing we wanted to prove. So, okay, now we have like written down the thing we want to prove, but how do we prove it? And this is where I come to the foundations of theorem proving, axioms, and rules. So, yeah, what kind of axioms are there? Let's look at this. So, I have like just a few of these axioms. So, like in actuality, there are quite a lot of these axioms that are being used, but I have selected a few so you can get a feel of like how this works. So on top, I have some axioms that deal with the discrete part. So, for example, in the top left, you have this axiom for the non-deterministic choice, where you have either the left-hand side or the right-hand side gets selected, so A or B. And this can be equivalently expressed in a conjunction on the right-hand side. And so, like, to you, it might not be obvious right now, but somehow this is the thing on the right-hand side is simpler. And yeah, this is something we will see later on as well. And then there are some other constructs to deal with the other program expressions. And also, we have some axioms dealing with differential equations. And the one on top, this is something that might be obvious to a lot of you. So if you have a differential equation and you want to see if like a certain formula holds after running this differential equation, you might just plug in the solution. So this is, yeah, for like a fairly simple class of differential equations, you can use something like this. But then the one on the bottom, this is, yeah, more interesting, I think. So this is about invariances. So you might ask yourself the question, so I have this certain property, and does this property get preserved by the differential equation? So for example, if you're starting in a circle, does the run of the ODE always stay inside of the circle? And the cool thing is that we also have a formula that can be equivalently expressed. And this, yeah, this is a little bit unfamiliar to some of you. So this star notation is, just signifies some higher order Lie derivatives in a certain sense. But I will go back to this point later on, why this is pretty cool, this formula. And then there are rules. So the thing I showed you earlier, these were axioms where you had equivalences, but these are inference rules. So on the top, you have the assumptions, and on the bottom, you have the conclusion. And these rules get used in a theorem prover behind the scenes. And I would just want to highlight one particular rule. And this is the loop rule that I have presented on the bottom here. And as you can see, in the bottom line, you have this star. And this star signifies a loop. And if you're using this loop rule, you can see that on the top row, where the A is, there's no star anymore. So this rule can be used to get rid of these loops. And this is with the help of these loop invariants. In this case, this is J, but we will talk about this. So the basic thing you do for these kind of proofs. So you apply these axioms on a top level, and then there are like two places where we need help. So one part are these loop invariants. So this is something that's really difficult to automate, to automatically find these. And as you saw earlier, this is also something we had to input into our checking algorithm. So this is sometimes where we need human intuition for these kind of proofs. And then the second thing is quantifier elimination. And I will talk about this. So let's first talk about loop invariants. Some things don't change. So this is the part where we had this invariant in our checker. So loop invariants have three properties. They are true before the loop starts, they are preserved by the loop body, and they imply the post condition. So these are a lot of words, so let's look at some pictures. So let's go through this. So earlier we wanted to prove that x is always greater or equal than 17. This is the black region right here. And then we have our assumptions. This is the blue region right here. And then now we want to visualize our invariant as well. And what you can see is that the blue region is inside the red region. So this is the first condition we had for the loop invariant. So the assumptions have to imply the invariant. And then the red region is inside the black region. So the invariant has to imply the post condition. And this is what it looks like. So this is a loop invariant that actually works. And then now let's talk about quantifier elimination. As I would like to say, Tarski's miracle. So there's this theorem that says the first order theory of the real closed fields is decidable. Okay, these are a lot of words, so what do they mean? So basically, you have statements about polynomials involving inequalities or equalities, and then you take some logical connectives like AND or implications, and then you can check whether these statements are true using an algorithm. And to me, this is quite mind-blowing. So let's look at a few examples. So this is your calculus homework, maybe. So the first line is maybe something you did in your calculus class. So you want to check whether a function is Lipschitz. This is decidable. So there's an algorithm that can check whether this is true or false. So you don't need to do this. Then there are two ellipses, and you want to check if they intersect. This is decidable. So your computer can do this. Or you might have some polynomial inequalities, and you want to check whether they imply each other, and your computer can do this as well. So I think this is pretty awesome that this somehow works. So to me, this is a miracle. So what are the implications of that? So how does that go back to our differential equations? So let's look at an example. So we have like a very simple differential equation that models like a free fall. And we want to show that well, check whether afterwards our position is greater or equal to 0. So we use our axioms to transform this statement. So we know the solution of the statement, so we can just plug in the solution, and then we have something like this. And now we have this quantified statements. So for this to be true, it needs to be true for all times. And then we substitute in our solution, and then we have this quantified statement. And the awesome thing is, we can just apply quantify elimination to this statement. And our computer will tell us this is wrong or this is true. And so we started with the differential equation question, and our computer told us yes or no. And this is cool. Of course, in this case, this is quite limited because we knew the solution. So yeah, it's boring. So let's get back to the axiom I showed you earlier. So the axiom on the right-hand side is also like a formula of real arithmetic. So this formula on the right-hand side, you can check with the computer. So you have on the left-hand side some like general invariance question about differential equations, and you can check it using your computer. So, and the cool thing here is you don't need to solve the equation. You can just check it automatically. So I think this is a really mind-blowing fact. So how does this whole approach compare to other methods? So on the first row, we have simulation. This is what we started with, and it's really scalable. It's really efficient. These are the tools that are available in Julia, but of course, you don't really get any guarantees if you have some uncertainty in your system. Then there's reachability analysis, which is not as scalable as like normal simulation because you're using some sets to propagate your uncertainty, and you only have partial formal guarantees because you are always limited because you cannot integrate over infinite time, and it's also available in Julia. Then analysis by hand, it's might not be really scalable, and you also rely on human accuracy for your proofs. And unfortunately, it's not available in Julia. And now, theorem proving is also only moderately scalable because we rely on this quantifier elimination algorithm. And as far as I'm aware, it scales doubly exponentially in the dimensionality of the problem. So yeah. But we have full formal guarantees, which is awesome. And now with my work, this is also available in Julia, but yeah, it's still work in progress. So in summary, theorem proving offers a new way to analyze your models. I think in the Julia community, we are usually relying on numerical methods, but this gives a new modality to analyze your model completely symbolically, which is pretty cool, I think. And it can be used to get formal guarantees for your models, which is oftentimes not possible with the tools that are currently available. And yeah, it's a great addition to the already existing tools. So you cannot like one big challenge is finding these invariants, and this is where other tools like simulation can help you come up with an intuition of systems to come up with these techniques. So I think like the future is in combining these tools. If you want to reach out, we have a Zulip, and if you want to know more about the theorem prover, we also have a website. So yeah, thank you.
All
right. So the answer might be obvious, but so in the case of nonlinear differential equations,
yes,
without an analytical solution, I assume the model won't work. No.
The model?
Or like the framework? Or
it works.
Oh.
It's like the ODEs can be like it can be in a very large class of Noetherian functions. So you have polynomials, you have sine, you have cosine, you have exponentials, and the kind of properties you can investigate are semi-algebraic, so differential inequalities and equalities of polynomials with conjunctions and disjunctions. So it's pretty general, but this is something that like a lot of numerical tools maybe can't offer. Yeah.
Have you tested it for more complicated models or ODE systems?
So there are case studies out there and available.
Cool.
Yes.
Yeah, very nice talk. Thank you. I didn't quite get, how did you put up this this invariant part in your example? How was that described? Or I mean, how did you come up with it? And what's the actual sort of role of that in your? You plotted it as this red thing, but where did that come from?
So this is, I guess, like this is the loop rule. So when you are, or maybe let's go back to the model itself. So this is something I didn't really talk about, but like in the not the last row, but in the row above this, you can see this star. And like in order to process this model, you somehow need to get rid of this star. And this is where these invariants come in. So this is the thing that doesn't change during the loop somehow. And this is where we need human intuition. So the way, like specifically for this example, I looked at some plots and I simulated a lot and so okay, yeah, this is maybe like a polynomial and let's try a polynomial. It didn't work. Maybe let's tune some parameters, and then it worked. And then like this is the cool thing. Once it works and it proves it's correct and I'm happy, but like coming up with these invariants is not easy. So like there's no general method to come up with them.
So just to follow up, is it something like an energy conservation law? Is that an example of an environment?
So yes, like this is one type of invariant, like the energy of the system doesn't change. But like it might not always be a useful invariant. So because you also have these two constraints. So it might be preserved during the loop body, but you also want it to follow from the initial conditions and imply the post conditions. So you might have some energy that stays the same, but it's like not useful for your proof. This can also happen. Yeah.
Next question, maybe the last one.
Thank you for the talk. Can you give us more of an intuition for the spirit of the core rule that you had there for proving the differential part of the proof here? The second differential rule, not the one where you have a solution, but the one that breaks it down in terms of the derivative.
Can you repeat the question?
Yeah, can you just give us like an intuitive sense of what that equation means at the bottom?
Oh, okay. So the way I understand it is, so you have your property, and if you're in phase space, like locally, you can always say, okay, I'm either like leaving this set where I'm in, like if, for example, if I'm on the boundary, and like my differential equation flow says, okay, yeah, let's flow into the set, that I know, okay, this is like at least at this point locally, I know I will go inside. And like if you do this symbolically, you can somehow we can somehow consider all of these points at the same time. And sometimes the thing is, like your derivative at this specific point might be 0. So then, like maybe if you had some calculus class in high school, you needed to look at some higher derivatives, and this is like, I guess, like kind of similar here. So the locally the derivative is 0, so you need to look at some higher order derivatives, and the nice thing is that at some point you don't have to look at higher derivatives anymore. So like this terminates. There's like not an infinite chain of derivatives you have to look at, but like this is like a finite expression, and this is like how it works, I think, like the intuition behind it.
All right, thank you.